And let me get back a bit about quantum programming model. So we have like a QRAM model, quantum random access machine model, which was defined for the purpose of conventions for writing quantum pseudocode. It starts at like, okay, exactly 30 years ago by Neil, very close by at NIST, right? And I would say afterwards there are some there are a lot of interest in defining quantum programming language, like QCL, QGCL, sorry, and QCL and QPL, scaffold, and Kuiper. You can see we have some like okay, PLDI paper. So PLDI is was playing friendly to the quantum, right? Okay. And let me also say something like Prakash and Mingshen case is called quantum wire language. They want to define something called quantum Hall logic. So the language is defined as, okay, you have skip, you have initialization, you have unitary, you have composition, you have measurement, you have while, refers to your question. So the triple they defined is like just a quantum, Hall triple is ACB, right? Here, they want to say that for every input state, which is generally 2 to the n times 2 to the matrix, satisfies some like a positivity property. So this is the triple is valid. They say like if trace A row smaller than trace B C row, C row it refers to the output of the state. Okay, so trace is this is just a matrix multiplication. So you see that, and trace just count the summation of the diagonal entries. And implicitly, you can see that this trace A row and trace BC row must be real number for being able to comparable. Okay. Super nice because it's quantitative, because it's able to track probability. You have inequality. Quantum computation, usually the advantage are not deterministic. Most quantum algorithms, let's say, has some probabilistic advantage. So you want to be able to reason about probability. On the other hand, the Hall triple defined is for the purpose of using classical computer to reason, right? And there are different reasons. You can say that, okay, current quantum computer is not very reliable, always have noise. On the other hand, like we're very familiar with the classical computer to do reasoning. This is our machine now, right? So the idea is, the reasoning usually is about, you can do like a different kind of reasoning, but one question you might be interested is like, we're given the circuits, use a classical computer to compute A from B. You're given B, you want to compute some good A, or you're given A, you want to compute some good B, right? This was never a problem in Mingshen's Hall logic. So let me take, I think I have enough time, so I want to go back here. You can see their first law. They are freely using matrix multiplication even if it's very large, right? Our observation, or our point is like the matrices are too large to scale within classical computer. 2 to the n times 2 to the n. So we are in a very awkward situation about quantum advantage because let's say reasoning is essential for validating quantum advantage because like we can easily make mistakes because of superposition, counterintuitive quantum features. But on the other hand, if we are not reasoning, our program are very likely does not provide us any advantage. So we need reasoning. But if we use exponential cost reasoning, would erase all the advantage. Okay. So let's clearly say that we are facing a scalability challenge. It's like we need trackable predicates, quantitative ones, right? So what property do we care? This is the question. And how do we choose them? Let me start from my previous paper with Jens, is quantum abstract interpretation. That's the motivation. So for quantum state rho and the qubit sets S, qubit sets S meaning let's assume rho is consisting of qubits from 1 to n, and S maybe like 1 to 3 or something. So rho S we denote it as a reduced density matrix. Bear with me 1 minute, I'll explain. So we want to be able to track a tuple of local reduced density matrices, and we use approximation. We use approximation of each reduced density matrix by a projection to track the system. So what is reduced density matrix? You can consider like a classical counterpart is like we have a very large, let's say 1,000 random bits, maybe correlated. And the classical analog of reduced density matrix is marginal distributions. You have 1,000 random bits, highly correlated, and I only care about 1, 2, 3. What's the marginal distribution, right? And the approximation, each reduced density matrix by projection is like we approximate each marginal by its support. Let's say you have a distribution, 3 bits distribution, with half probability all 0, half probability all 1. Now I only care about all 0 or 1. I don't care about whether it's half or something. That's an approximation, right? I was extremely satisfied when we had this paper because, that was my passion then. But then Jens kept asking a question: can we do better? What do we miss? So this is qualitative. Which only being able to answer yes or no. And it cannot track probability. Okay, so now we have like 2 tools together, right? We have quantum Hall triple, quantum Hall logic, and quantum abstract interpretation. And for quantum Hall triple is ACB, right? I restate everything here. And quantum Hall logic, so it studies general predicates like AB between 0 and 1. Between 0 and 1, you can say the matrix version, 2 to the n times 2 to the matrix version. Extremely bad, but it's quantitative, super good. So for quantum abstract interpretation, it's local projection, scalable, very good, but it's quantitative, only being able to answer yes or no. So we want them to be able to marry. Oh, sorry, let me say one more words. So you can see the way that they are, the QHL is being able to track probability is like A and B is between 0 and 1. Anything between 0 and 1 is continuous. So we are able to track continuous objects. Second time. So then we provide something called a local observable. So we do care about the tuples. So we have AS1 to ASM, or we have BS1 to BSM, right? You can see that each S1 or to SM, they only care about marginals, quantum marginals or reduced density matrices. So as long as we not choose this size of SI too big or this M too, if size of MI is not too big, or size of SI is not too big, then the whole number M cannot be too big, let's say, right? So generally, we are able to be, say, doing something like efficient representation like quantum abstract interpretation, but not like a QHL, right? And we also being able to do quantitative reasoning like a quantum Hall logic, but not like a quantum abstract interpretation. We still use this like version like a trace A rho smaller than trace BC rho, okay? So the judgment now becomes this A is defined in this linear combination way of ASI, and B is also defined in the linear combination way of SI. To support my argument, we can easily compute to see that trace A rho in this version would mean only depends on rho S1, rho S2, rho Sn, only depends on the tuple of quantum marginals. And so does B sigma. Seems good enough, right? Now we focus on quantum circuits with only 1 or 2 qubit unitary gates, and we would borrow or like just use the rule of quantum Hall logic is like this. ACB is equivalent, or like this rule is like if A is smaller than U dagger BU. This is a matrix inequality. So the rule is QHL rule. So only the shape of A and B is restricted. We no longer care about arbitrary A and B. We care about this class of A and B. This provides us scalability. Seems good enough, right? But I need to spend the next 5 minutes. So very simple example, let's say we have a C0 gate. If you remember, like the C0 is a black dot and the square plus. Oh no, the circle plus is like if the first qubit Q1 is 0, it does nothing. If it's 1, it does not on the second bit, right? So simple. So you can clearly see that if with the input 0, 0, because the C0 would not apply. Because the first bit is 0, it would not apply the NOT gate on the second bit. Very sadly, the logic or like the rule itself cannot help to prove this thing. Even if we have like an exponential, even if we allow arbitrary computational power. The statement is just cannot support us to prove that, okay, if your input is all 0, your output is also all 0. Or some inequality like that. Moreover, like we're not even able to prove very, very simple thing for this extremely simple example. So the question comes from, for all input, this is extremely strong because most quantum algorithm has a fixed input or 0. So this is the true marriage between QHL and QAI. So you can see the judgment type comes from the QHL and QAI, makes us to restrict the shape of A and B. But we also need the quantum abstract interpolation, P and Q, as a support to say this inequality, I only care this inequality to be valid. This inequality to be valid when the state is in this shape. Right? So this says like if your input satisfies this P, and then your output will satisfy Q, and also you have this inequality. Okay, this is the logic. And you can see no magic, no magic, no magic. The key part is 1, and 2 is kind of reuse of 1. Right? So the workflow is like this. Okay, for given specification or precondition of circuit and circuits, we choose the domain first, S1 to Sm. We approximate the given predicates by the shape predicates, and we apply the rules to try to get something. Okay. Now we are able to prove anything of this C0 without using too much efforts. And we are able to reason about these GHC circuits. We're able to say like the output would satisfy this form, and this 1 over square 2 was never being able to obtain using QAI. But with this quantitative, we are able to get this 1 over square 2, but we're still missing the phase factor. So this is way beyond, this circuit also way beyond the simulation of unitary. And we could also do like a quantum phase estimation. Okay? So there are some future works possibilities, like we can care about more circuit families. We can do programs with measurements and classical control, and we can mechanize proof search. And we would like to pursue with like this mechanized proof search and integration with symbolic tools like VYZX and VOQC. So Robert will talk about this one. I think I'm right on time. Thank you very much for your attention.
All right. So now we'll take questions. Just raise your hand and I will pass the mic around.
Hi, so please correct me if I'm wrong. I would love to know what all symbolic operators can you then support? Like you talked about like identities being like sort of supported directly, allowing you to have like this scalable verification possible. But is a way to then like handle any kind of control on an operation where you have some outer product for some control value or something like that?
Can
but
you say it again from the very first sentence?
Oh, I was saying like, can you what all like symbolic operators, etc., can you sort of express? So for having like scalable verification here.
So you're not asking for this future work, it's about our...
I mean, like saying like what could happen there is I think my question.
You want to see
there.
what could happen there?
Yeah. What all options do you think could be pursued with symbolic tools?
I don't know. I think maybe after Robert's talk, I would have clear idea.
That makes sense.
Thanks.
Any other questions? All right, we'll do one more, and then we'll go to the next talk.
Thank you for the great talk. I wonder if I use this tool, then I wonder if I can check the like BQP algorithm is really BQP or not.
You want a BQP algorithm?
That is
right. You want to be able to verify BQP algorithm, right?
Yeah.
No. So there's a hardness result to say like even if you only want to track a single qubit output precisely or with very high precision, you would go beyond to you wouldn't. This question is QSZK complete, quantum zero knowledge complete, quantum zero knowledge proof complete, and so you need to sacrifice some like precision. But if you care about shallow circuits, you can refer to our work with like Tom on Uppsala 200 last year, which says like for any shallow circuit, you can do things completely without any gap and very precise. Yeah, so maybe you want to restrict your competition with some subclass. Thanks.
All right,
Thank you.
Next up, we have Christophe Charton. He is a research engineer at Université Paris-Saclay, and he's going to be telling us about
Yeah, this is already better. At once I keep it this way and Okay, so thank you, Sarah and Nenkun. So indeed, yes, the article is about symbolic execution of quantum programs, and in particular quantum programs where there is also measurement and classical control. So the basic idea is that testing, debugging, and verifying quantum code is something that is hard. And to do so, our basic strategy is to rely on symbolic representation and symbolic reasoning over the programs. By symbolic, I mean a kind of reasoning where at some point there are some parameters that are left free in the representation. And so symbolic reasoning will hold for any possible value of these three parameters. So it can be the input that we give to the circuit, it can be a probability of something happening, or it can be a path in the superposition of the state. Here I will present the symbolic format for representation that we are using. It is called hybrid path sums. And I will tell about the implementation that we made of this format and present some experimental results that we got from this work. So first, again, and it has already been said, simulating something that is quantum is hard. And yeah, basically, we get some exponential data structure as soon as we do something to a quantum register. So when it is only unitary, it is hard, it is exponential, but things even get worse. Whoa. Okay, so there was something on this slide, but something happened. Basically, it is harder when you get to something that is hybrid with measurement and classical control over it. Because when you measure, you have to consider the projection of your operator. Maybe this projection that you have to consider in parallel are in exponential number, and then you have to deal with the renormalization and so on. In addition to that, it happens that actually what we call a quantum program at some point in the day turns out to be something that will be implemented as hybrid. Because maybe there is this thing of hybridization, maybe you care about how long you will request your quantum register and you will try to make it short as possible and to insert more and more classical things into your unitary if possible. Or maybe you want to perform some error correction, and here it is a complete intertwining of things that are unitary and things that are classical and that rely on the measurement. Yes. So we want to verify this, and it appears that in the quantum context, it is very hard and maybe not reasonable to rely on the standard strategy for the classical case that is based on assertion checking and test. Assertion checking doesn't work because there is the destructive measurement. If you want to test an assertion, you have to look at the state to measure it and to destroy the superposition. And final test doesn't work much better because what you want to test at some point will be a distribution of probability between different things that may happen. Maybe these different things are in exponential number, and so you will need a huge number of runs to get something for testing your distribution of probabilities. In addition to that, these methods presuppose that at the development time, you already have access to the quantum unit, which is far from evident in the usage scenarios that are considered. So instead of that, we promote and we develop tools that are based on static analysis, where there is no basically static analysis. By this, I mean that there are methods where you execute the code not directly on a quantum computer, but on a classical machine that will interpret it as a code working on something mathematical, on a mathematical representation. So there is no need to execute in the sense that you don't need to address directly the QPU. And also, instead of providing a statistical argument that you have great chance to believe that your specification will be met, you will get an absolute and mathematical guarantee that the specifications are met. In addition to that, you can also insert some symbolism in your specifications and your code, and in this case, in one run of verification, you have the guarantee for any possible value of the parameters that you have left free in the verification process. So, To do that, we need first to have a compact and tractable representation for the hybrid quantum classical programs that we want to verify. And here the strategy is very simple. It starts from observing that thanks to Mathieu in 2019, we have a compact and tractable representation for purely quantum computing. And so the strategy, this representation is called path sums, and here the strategy is to take path sum and to extend them to the hybrid case. One word about the path sum in the unitary case first. So I like to start with this very standard description of the order finding in the Nielsen-Armstrong manual. So the algorithm is described as a sequence of operation, and in the presentation of the algorithm, it is intertwined with some almost formal, I will say, description of the evolution of the state of the system along the operations. And if we zoom in, this is a sum of this description, but basically there are some common patterns or common things in the way it is described. So typically we have a normalization term at the beginning that is encoded via an integer, and then a sum of things, here a big sigma, and each of these things is indexed by reference to the binder of the sum, and in each of them there is something, a factor that is elevated to the complex exponential, so a phase factor, and a pointer to the computational basis. And the idea of path sum is just to give a precise and formal format to this generic pattern. So in path sum, we don't consider the whole sum anymore. We just take one generic symbolic element in this sum that we call a path, so it is a symbolic path, and we also get rid of the complex exponential things. So we just keep what is necessary to identify a state. So we have the integer parameter that gives the normalization term and the binding of the sum. We have a phase polynomial that is given by a symbolic d-adic fraction, and we have a set of binary functions for the output element in the computational basis. And so we can just keep these three very simple and standard data types and run the whole analysis of a program, here unitary, in this format. So we have to remember the green, the blue, and the red element. Each of them, each elementary gate has an interpretation in this format. Then it is able also to interpret some circuit combinations. So here the sequence and the parallelism. And so we can run, I had a picture there, but not anymore. We can run the full analysis of a quantum circuit, just caring about the standard data types elements. In addition, the theory is also provided a set of rewriting rules. So basically, these are tools enabling to compute the destructive interference between passes. And we have some rules that we can apply as rewriting of our path sums. And what they do is they discard or they eliminate the passes that interfere destructively together. Okay, so this is for the unitary case. Now, again, we are interested in the hybrid case. So there was pictures again in the slide. Sorry about that. So what we want is to be able to analyze a hybrid where there is measurement and classical control. And here, the basic idea is quite simple. Is that path sum, what they define are a set of passes, and individually, each of these passes lives in a vector from the computational basis. So each of these passes yeah, it is like if it has already endured all the possible projections. And so to analyze, or to analyze or to represent the fact that at some point one data cell in the PASM is no longer, has been measured, so is no longer something quantum, but is something classical. Basically, what we need to do is just to partition and to filter all the passes along the measurement scenario they belong to. We call them worlds, following some tradition, taking birth with Hugh Everett works. So, yes, sorry about the representation, but basically, when we run a circuit and we want to say that this data type is no longer a qubit but a bit, all that we do is to mark that this is now a classical data. And it doesn't change anything. We can follow on the analysis in the hybrid PASM format, and it is only when dealing or when trying to get an interpretation of this in the Hilbert space that we will have to care that this is a quantum data and this is a classical data, and so to decide which of the passes are going to interfere together. Okay, so this is the principle of hybrid PASMs. We have some work for the extension of the calculus to this hybrid case. So here some rules to deal with the computing of interference. This rule has to care that we don't consider destructive interference from passes that don't belong to the same world. So there is some adaptation that had to be made. And we also designed some rules and some reasoning tools enabling to deal with the tensorization of states and the discarding of information from some of the registers, which is something that comes very straightly as soon as we are concerned with hybrid programs. We derived a core assertion language from this format. So very quickly, we are able to give a full description of the state of the system in classical and quantum registers. We can also talk more locally and describe describe the state in some parts of the registers. And we could also derive some probabilistic assertions. So basically, an hybrid PASM encodes a set of worlds, and we are able to talk about within this set of worlds the probability to be in one of these worlds such that it satisfies a given condition. Okay, this was the quantum phase estimation. Again, I missed the figure. What I want just to underline here is that we can run an analysis to the gate-to-gate composition of a quantum circuit, and then we have a specification for a big unitary, and then this specification itself is used as a parameter for an higher level function. Here it is a bounded version of the repeatancy success, so that we are able to design and to specify the repetition of a non-deterministic experiment. So with some bands. Okay, so I have my experimental results. Some comments about that. So this is about the phase estimation. As we see, when it is just about computing a probability from the unitary case, the format is very performant, and we gain several orders of magnitude with regards to the state of the art. In addition, and I think from what I know, it was the first time in the literature, we could plug this analysis in this higher level function of bounded repeatancy success. And here, for example, in a bit less than 3 minutes, we were able to compute the probability of satisfaction after trying the phase estimation over 300 wires with 10 different tries. Further experiments here with one interesting feature, and I won't develop on that, but the formalism is also able to formalize non-deterministic processes. And so we could formalize and play with some very basic examples of quantum error correction. So here is the 3-qubit code. And so it gives us great hopes that this formalism could be used for more scaled version of error correction. And we also use the tool for some experience on the equivalence relation on unitary circuits based on some standard versus mutant version of the quantum Fourier transform. And here again, we had a good scaling result with the possibility to handle up to 500 qubits. Okay, so in a nutshell, we have this compact and tractable representation format. It is quite flexible, enabling to deal with low-level gate-to-gate composition and also higher-level function. We performed experiments on various different interesting patterns from the literature, and we have good hope and exciting perspective of going further with the exploring new patterns. And yes, and also I give you the URL for the tool, and we have also a nice tuto with some lacking pictures here, but we have the representation of the circuit and some interactive mode that enables you to have some beautiful pretty printer and to build your hybrid system.
All right, let's thank our speaker. I don't want to run too far behind, so maybe we can take one question max. Anyone have any burning questions?
So the Kubrick's paper, the big leap over Matt's original path sums is that you had symbolic reasoning, and you talk about symbolic reasoning here too. Did that create problems for checking that you're in different worlds if you don't have a concrete state?
Sorry, I'm not sure I understand. So there is something between the question basically is about the link with the original Kubrick's paper.
Yeah, so maybe just does this fully generalize Kubrick's?
Somehow, but Kubrick's was about, parameterized proof where there was no register size. It was left free, and then the user had to put some effort to make the proof. And here it is about fully automatic proofs over some instantiations of the circuit. So it's a kind of different perspective.
So it is concrete in that way.
But at some point, there may be someone at some point will make the two approaches merge.
Yeah.
It may happen.
Thank you.
Thank you.
All right, let's thank our speaker again. Our next talk is on VYZX, a formal All right, so now we have the final talk of the session. This is also a distinguished paper. It is titled Cobble, Compiling Block Encodings for Quantum Computational Linear Algebra. The author of the paper is Charles Yon. He is an assistant professor at University of Wisconsin-Madison, and he is currently looking for motivated students to work with. And so, without further ado, I will let him explain the work.
Thank you so much, Sarah. And hi, everyone. I'm really honored to be awarded for this work. Today, we are going to talk about how to program quantum computers to solve linear algebra problems very efficiently. And so part of what I mean by that is that over the last couple of years, we have seen a blossoming of these quantum algorithms for all sorts of interesting applications, ranging from solving systems of linear equations, solving differential equations, simulating physical particles, and even doing things like statistical regression. Right? So the kind of the bread and butter of modern data science, MLE kind of applications. So one thing you may know about quantum computers and quantum algorithms is that they promise asymptotic speedups over what classical computers can do in these applications, up to exponential speedups. And in this case, for something like inverting matrices, solving linear equations, we do get an exponential speedup under favorable conditions. So you can see that it's exponential because the quantum complexity is polylogarithmic in the dimension of the matrix in. That's to be compared with the classical complexity, which is going to be polynomial in the dimension. Right? That's where we get that exponential speedup claim. What you may not know, even if you're familiar with quantum algorithms, is that, believe it or not, a whole lot of other quantum algorithms out there, things like Grover's algorithm for search, that don't look like linear algebra at first, actually can be represented as a specific matrix computation you want to perform. Right? So it kind of gives us a unifying picture of a lot of these quantum algorithms, even though we're not going to have a time to talk about them today. So all of this, great news for the algorithms world, but what does it have to do with programming? Well, one of the things is that, believe it or not, almost none of these algorithms has ever actually been written down as an actual program that could run on a hardware quantum computer. So why is that? Why is this problem so difficult? Well, to see why, let's put ourselves into the shoes of a quantum programmer, open up one of these papers, and look at what the paper gives us. It's not pseudocode, it's not an algorithm listing, it's just math, a whole bunch of equations that take the form of something like this. We want to compute a matrix function, A inverse, e to the minus iat. And what the algorithms paper tells you is all of the math that's necessary to decompose that matrix function into primitive operations, addition, multiplication, these sorts of things on matrices. Right? And eventually, when you get down to the base case, you even have to decompose your input matrix A into things like smaller matrices, all the way until you get down into primitive logic gates that will be provided to you natively by the quantum computer. So every step of this process, representing and constructing a matrix and then building up all of these linear algebraic computations, is a programming challenge. And what do I mean by this programming challenge? Well, there is a first problem here, which is the gap in abstractions that we have available to us as programmers. If you wanted to take the paper representation of a quantum algorithm and make it run on hardware, you eventually need to get this thing, which is a quantum circuit, individual logic gates executing on individual qubits in the system. So how can you do this? Well, today, if you are a programmer, you could use something like IBM's Qiskit framework, which is a Python-based framework in which you can just write code that specifies, it lists out every single one of those little squares in the picture there. Right? That is a form of programming that we have today. And it's really nice for a lot of algorithms, but what if I told you that it is possible to build higher level programming abstractions in which you essentially just write the same notation as the algorithm designers intended and leave it to the compiler to automatically generate the actual sequence of logic gates? That would save us a lot of work, and it is indeed what we are trying to do in this work. Right? So that is the first problem here. We want to be able to close this abstraction gap, get the circuit from a suitable high-level language. But even having the circuit in hand is not enough, because we have very small quantum computers. We want to make these circuits as small as possible, as few gates and as few logic gates as possible, so we can run it on the nearest term computers that are coming online. what can you do to solve this problem? Well, today you could take one of these off-the-shelf existing quantum circuit optimizer tools. Right? There are a whole lot of them now in existence. Some of them have been published at PLDI. Our experiments show that given circuits of these applications, they typically see something like a 30% improvement in performance. What if I told you that by exploiting higher level program structure, you can get instead 95% speed up? Now, this is not going to be global for all circuits, right? Generic circuit optimizers don't have program structure. They have to solve a much harder problem. But if we have a suitable high-level language, we can exploit that program structure and get really good speedups, right? So, before I continue, I want to spend a quick minute or two getting everybody on the same page as to how these quantum algorithms work. I mean, why should a quantum computer be so good at linear algebra? Well, the short answer is because quantum computers are linear algebra. We've seen so far some definitions of these qubits, right? Quantum analogs of bits. They can exist in these states which are called ket0 and ket1, which are actually just vectors with complex coefficients. Here, ket0 is 1, 0, ket1 is 0, 1. The cool thing about qubits is that they can exist in superposition, so 0 and 1 at the same time. And mathematically, a superposition is just a linear combination of vectors. So we can have two arbitrary complex numbers in those coefficients there, just linear combinations, just some linear algebra, right? So if I have this sort of construct, I can already start thinking about how to generalize this to encode arbitrarily large vectors, not just vectors of 2 elements, but of n elements. There is a rich study of how to do this supposed amplitude encoding step. I won't have time to explain all of this. There's actually a lot of deep theory here. I'll refer you to the paper to see the details, but it is the general idea of how you can represent vectors on a quantum computer using a very small number of qubits. Now, given qubits, what can we do with them? Well, one thing we can do is to measure them. Measuring a qubit collapses its superposition and gives us a classical outcome, either 0 or 1 with some probability. That probability happens to be derived from the square of the norm of the complex amplitude. So negative 1 over square root of 2, norm squared turns into 1/2. Right? So measurement will collapse the superposition of the qubit, making it not quantum anymore. So we don't want to be doing that all the time. Instead, what we want to do are these quantum logic gates, which can manipulate the state of information without collapsing it from superposition. There are a whole lot of logic gates out there. For example, there's a quantum version of a NOT gate. It has a denotation, which is a 2x2 unitary matrix that multiplies by the vector. And in this case, what it does is it permutes the coefficients to turn ket0 into ket1 and vice versa. There are more interesting gates out there that do things like create superpositions, like this Hadamard gate here. And you can even have bigger matrices. So for example, you can do conditional logic. This controlled NOT gate will flip the value of the bottom qubit only if the top qubit is equal to 1. So you can imagine that this ends up being represented as a 4x4 unitary matrix over 2 qubits, length 4 vectors. Right? So that was a lightning-fast introduction to quantum computing. I want to move on to talk about some of the research contributions here and start by covering how we build a language to close this abstraction gap. So what makes representing matrices hard on a quantum computer? Well, how do we even represent matrices on a classical computer? Well, I don't know about you, but when I see a matrix, I probably am tempted to take that matrix and write it down as a whole bunch of floating point numbers represented in my random access memory, right? A whole bunch of arrays. Whether the array is dense or sparse, it doesn't really matter. It turns into a bunch of arrays, and we have all of these nice for loop-based iteration patterns that we can use to perform operations like matrix multiplication very efficiently. You get enough of those, you package them into something wonderful like BLAST and LAPACK, you publish it out there, and you get a whole world of matrix arithmetic. Of course, arithmetic whose scaling is polynomial in the matrix dimension in. The whole point of doing it on the quantum computer is to make that faster, right? It's to have this polylogarithmic representation. And we've already seen how a quantum gate, being natively a matrix, ought to be able to do this for us. So whenever we have these matrices, we're just going to write down a small number of gates that implicitly, through their semantics, represent the matrix we care about. And then we're going to have to figure out what the corresponding computation, what the programs are going to look like. All right, and that is going to be the goal of this cobble system. Figure out the quantum analog of BLAS, NumPy, and such. So let me show you very quickly what it is like to program in this world. We're going to take that kind of mathematical notation that you might find in these algorithm papers, and the compiler will generate for us the circuit given that program. Right? Just a couple of observations about the circuit. You can already tell it has some compositional structure. There's some sub-circuit corresponding to A for B, and eventually you get down into these primitive logic gates. In this example here, they're X and Y. You can't go break them down any further. They're just going to be the native operations that the device already gives you. All right. So rather than harping on about the technical design here, I want to motivate the design by asking an open-ended question. Which matrices do we hope to be able to efficiently encode as programs into a quantum computer? It's a very open-ended question, and indeed the theory community spent like 10 years trying to answer it. They finally managed to do it in around 2019, where there were 2 landmark papers that were published, showing 2 apparently contradictory results. The first one is that there is no hope of doing this for arbitrary dense matrices. You cannot take arbitrary matrices and encode them efficiently into a quantum computer. But the dual of this is if your matrix has structure, if it's particularly sparse, particularly repetitive, built up from smaller matrices, then there is a constructive way of actually doing this. All right? So that is going to be the basis, ultimately, of our language design. Of course, we want to use these gates, those matrices, to represent the matrices we care about. I mentioned this unitary thing, right? The semantics of every gate is a unitary matrix. What is a unitary matrix? Well, it's some kind of linear, norm-preserving, diagonalizable eigenvalues unit, that sort of thing. But the thing that's interesting about it is that unitary matrices are not closed under arithmetic operations like addition. Some of unitary matrices is not necessarily unitary. That is a massive pain if we want to encode arbitrary matrices that we care about in this framework. Fortunately, once again, we have an answer from the theory community. It's called a block encoding. Right? So what a block encoding is that given an arbitrary, possibly non-unitary matrix A, we're going to shove it into the top left block of a bigger matrix, B of A, such that the other 3 blocks of the matrix are allowed to be arbitrary as long as this whole big matrix is unitary. This is always possible, subject to a mild condition that the entries of A are not too big. If they are big, you have to divide the whole thing out by a number alpha, which is called the subnormalization. Remember that term. It will come back, subnormalization. Right? It's definitely related to that. So in this case, the lower bound here is going to be the spectral norm of A. So one cool thing that we can do with a block encoding is that we can perform all the matrix operations that we want, for example, matrix vector multiplication. We have a block encoding of the matrix A and an amplitude encoding of the vector X. We want to get an encoding of the vector AX. We can do this by taking that block encoding and applying it as a circuit to the state X, along with a couple of extra qubits, and this will give us a resulting superposition. It'll be either 2 things. It will either be AX, along with our temporary qubits being 0, or our temporary qubits are not going to be 0, and we're going to get some garbage state that I'm going to denote bottom. We don't want that garbage state. We want to get rid of it, and the way that we'll do that is by performing a measurement. We're going to measure our temporary qubits. If they come back all 0, we know we're good. If they come back non-zero, we have to start over from scratch. And the number of times that we have to start over turns out to be proportional to alpha. Right? So alpha, subnormalization, is not just a technical little thing. It's actually directly proportional to how slow these programs are. All right, so this is the basis of our language design. Once again, we're going to start with these unitary gates. Those will be our base case. And inductively, we're going to add these operators here that enable us to compose these matrices together. And eventually, you get a whole bunch of semantics that you can look at in the paper. Okay, that defines you, the language. All right. So that's what the language looks like. Let's talk about how to make this language efficient, right? How to close this efficiency gap. First, we have to talk about how to measure the costs of these programs at all. One thing we could do is count the number of gates. In this case, to simplify things, we'll just count the number of x's and y's. We'll leave everything else as a footnote. Now, the thing is, as I just said, it's not just the number of gates that matters. It's also the number of repetitions of the program. This subnormalization says we have to multiply all of our costs by alpha. We're essentially repeating this whole process. So our actual cost is going to be the number of gates of the circuit multiplied by this subnormalization. That's the thing that we're going to have to minimize. The good news is that it's not too hard to compute these subnormalizations. Indeed, prior work gives us some ways of essentially just inductively going through a computation, just calculating it all, and we can figure out exactly how many repetitions of the program that we need by looking at the program. This is a very simple example that kind of gives you the idea. In our full paper, you can see the cost model of how to do this. There's actually some kind of intricate math involved with polynomials. Please ask me offline if you're curious about how all of this works. Unfortunately, I'm a little short on time. I'll take questions at the end. So in order to reduce the cost of these programs, then what can we do? Well, it's a simple idea. We're just going to combine some like terms. We're going to make these programs shorter, which is going to end up having the effect of reducing the subnormalization. Right? So this is a really great idea. And you can see that by doing this, you just get a shorter circuit. Shorter program, shorter circuit, right? It's pretty logical. But does this idea have limits? Okay, so here's another program from a different application. It corresponds to this circuit. By looking at it, you can kind of see, okay, maybe we can combine some like terms. And here is what happens. Right? You get a shorter program, but you actually do not get a shorter circuit. That's kind of surprising. Why is that? Well, partly because the idea of sub-expression reuse no longer works on the quantum computer. Think about this expression. Classically, we can evaluate this expression by just performing one addition instead of two. You take a plus b, you square that, and you're done. But the quantum circuit has to perform both additions. It's just like a whole bunch of things one after the other. And even worse, right, if we're talking about things like exponentiation, right, the circuit is actually really disadvantaged because it can't cache and reuse anything. All right. This doesn't mean that we are completely hosed. There is some deep math that we can tap into here. There's something called the quantum singular value transformation that I absolutely do not have time to explain. But a way to think about it is that we can exploit some linear algebraic structure, kind of analogous to diagonalization, right? Exponentiating a matrix is a lot easier if you just want to exponentiate the diagonal instead. This gives us some really good theoretical properties, but it requires, believe it or not, a whole lot of PL work because we have to do things like constrain the properties of the matrix and the polynomials of the matrix, and we have to figure out whether these exponents exist in the first place. All right, so the bottom line is we are able to build these things into our type system and a system of program level rewrites. We ultimately make it so that we have an intermediate representation that efficiently captures what's going on in this program and generates a much shorter circuit. And if it looks easy, well, it's really not because there's a whole bunch of stuff that we had to do in the paper. So just to finish up real quick, you know, the evaluation shows that our system is able to accelerate a whole bunch of interesting programs. And moreover, it's able to outperform some of the generic circuit optimizers that, like I said, are fundamentally solving a harder job, so this shouldn't really be surprising. I want to end the paper on this final note. You know, I don't want to claim that we are ready to replace the classical linear algebra and high-performance computing stack, right? This is really just the beginning. But what I think that it is a call to action for the programming languages community. Because what we have seen in quantum computing in the last 5 years is tremendous progress in hardware and in algorithms. The software has yet to catch up. And there's a really great opportunity here for us to build better abstractions so that we can better write, verify, and reason about these programs. So with that, there is some code available. Happy to take any questions.
All right, so take a few questions here. And also for all of the people that spoke in this session, if you can just stick around afterward a little bit in case people have other questions, that would be great.
So I feel like the alpha rescaler that appeared and that you talked about for a little bit is really important towards the question of summation and the question of running time in a way that is not clear to me. Is there any sort of intuition you can give there?
Yeah, it's really surprising, right? Because it seems as if it's just like a technical factor that goes in there. But, I mean, at least you can look at the math. I mean, Robert, hopefully this math will give you a little bit of intuition because the alpha, here I wrote B of A, but technically it's actually B of A over alpha, right? So the alpha ends up propagating over there where it becomes an amplitude, and amplitudes become probabilities. So that's why our success case ends up being linked to alpha. I wish I had something that was less mathy as an explanation. You know, let me know if you think of anything.
All right.
Yeah.
Thank you.
Take one more question.
My question was, please go to the addition of alpha.
The addition, was that the example, this one? Yeah.
I mean, the alpha equation is not optimal, so in some sense you actually can provide some upper bound on the largest eigenvalue. And I believe this is generally hard to compute the largest eigenvalue. This is more or less like a comment.
You're absolutely right. It is an upper bound, right? Knowing nothing else about the structure of the program, this is the most that we can say about the number of iterations that you'll need. Something that I really want to do is precisely to incorporate additional information about the structure to give a less coarse upper bound.
All right, let's thank our speaker again. And if there's any, thank you for attending the quantum computing session. If there's any questions you have for our speakers that you want to take offline, you can find them up front over here. Thanks again.
Yeah, hi. So for quantum fans, tomorrow at 2:40, we'll have another quantum paper on equality saturation for quantum circuit optimizations. So please come if you are interested in that.
Okay, so we're going to go ahead and get started as it's 2 o'clock. So I'm Ileana Subotovic. I'm happy to welcome you on this session of static analysis. Maybe someone in the back could close the door because otherwise there's a lot of noise from the hallway. Thank you. And so we'll get started right away with Byron Zhang telling us about flow-based analysis.
Great. Can everybody hear me? Good. All right. Hello, I'm Byron Zhang from the University of Chicago. Thanks for the introduction. And I'm here to present our recent work on closure optimization. This is joint work with Professor Olin Shivers from Northeastern University and my advisor, John Repu, who's in the audience today. Let us start with the subject of study, the closure. So a closure is a code pointer together with an environment, as we all know, which maps variables to values. It is needed to represent a higher order function value in our languages. And the question then we're focusing on today is how we should represent that environment. And the simplest representation, which is also the most widely used representation, is a flat closure. So let us start there. So consider this function. I'm going to use ML-like syntax for this talk that closes over in fact, 5 variables. And together with the code pointer itself, which I'm going to use the superscript C to indicate that K3's closure is represented by the 6th tuple. Now, so K3 is defined in the body of another function K2, which inherits all of these free variables, but except for Y2, which is bound by K2. Now that its closure is represented by this 5 tuple. And now we do this again. If this is wrapped around in another function, K1, this inherits all the other free variables, plus an additional variable C that it only itself uses. And finally, we have the top-level function G that closes over everything, which is not particularly interesting here, so I'm going to omit it from now on. So what does the environment look like under flat closure? It is very simple. The environment is just a tuple of free variables. And despite the simplicity, it has actually 3 really nice properties. First of all, it's really easy to implement, and we don't like to make our life harder than it really is. But second of all, the variable accesses are very cheap. So say if K3 needs to access the variable A, it can do so via one load away from the closure pointer. And depending on who you ask, this is maybe the most important aspect of this. This is proven to be safe for space, which we'll come back to this point in a little bit, but roughly this means that the closure only points to values that it actually needs. But the downside of this approach is perhaps very visible in this diagram already, which is that every new closure repeats part of the environment because they're all free in this. Not only do you have to allocate bigger tuples, but you have to copy values from one closure to the other to another. That is one load and one store for each free variables at each level, which is less ideal. But before I continue with the talk, you may be asking yourself, who cares? Who writes code like this? Right? Fair point. This is extremely hard even for vibe coding tools to generate. But compiler frequently generates these type of patterns, right? One example is, we all know, it's monadic style programming. So say you have this do block here. Each one of these arrow operators, we want to call it, will be desugared into a deeply nested function, which propagates all of these free variables up. A second kind is currying. This should be obvious. That currying defines implicitly a deeply nested functions, which propagates up its free variables. But the reason why we care about this today is because of Standard ML of New Jersey. And there's one particular point about SML New Jersey that I want to draw your attention to, which is that it not only uses a CPS-based IR, it also uses a CPS-based runtime system, which means that instead of using a stack to keep track of calls and returns, we use continuation closures to do so. Which means that the closure representation for those continuations has a tremendous impact on the actual runtime. But regardless of how you get to this point, once you're in this point, what can we actually do about this? And we realized that A, B, and K are not actually used in K1 or K2, but instead just there to provide access for K3. So an obvious idea is that we're going to allocate a shared tuple, that, that captures these values, and then we just put a pointer in each one of these closures. So now the closure construction is cheaper because it's 1 low versus 3, but the variable access becomes more expensive. Now that when K3 needs to access A, it needs to do so via a layer of indirection. And it's also important to note that closure sharing does not describe one unique representation like the flat closure does. Is in fact a family of representations, right? As another example, we can see that Y1 and the pointer is shared between K2 and K3. So it's an equally valid choice to put that into a separate tuple. It's not a particularly good choice here, just because it's not big enough, it's not reused frequently enough to actually make a benefit, make an impact. But this highlights the fundamental trade-offs that we're facing. It is that we want to minimize allocations at the same time of minimizing the level of interactions. There's another choice that we can make, which is perhaps a little bit more problematic, which is that we see the C here that is available at the time we construct the closure for K1. If we were to move C inside of that shared tuple, so we did something really nasty here, right? By putting C in the shared tuple, we keep C reachable after it is semantically dead. So what used to be collectible after K1 has been dead, now it is not collectible anymore because K2 and K3 has access to that. This is a space leak, and it's violating this compiler's space safety guarantee, which is not good. At the same time, we have a third choice here, which is that if we somehow find out that K3 is called more often than it's constructed, so for example, if K3 is the last stage of a curried function that we've shown here, which is applied in a loop, we may decide to revert back to flat closure conversion for that ease of access. This will create more allocations, obviously, but the access are cheaper. So this is what we call the closure compaction, which is we choose not to reuse a shareable closure when it is available. So under closure sharing, what does the environment look like at runtime? It is very permissive. The environment is now a DAG with a root, which is a pointer to the closure, from which your free variables are reachable. And we talked about the trade-offs here, and the concerns that we have is that we must balance that trade-off and must not introduce space leaks. So if we widen our imagination just a little bit more and say, why do we have to confine ourselves to using one variable to represent a closure? Why does the graph has to have only one root? Well, it doesn't, right? So that's another idea, an orthogonal idea, if you will, of optimizing closures, which is what we call closure spreading. So instead of using one variable to represent, say, this K closure, which is represented by a tuple, we can just simply use, say, 4 variables to do so. Now that every single one of these free variables are variables in the programming language, which will map to registers by the backend. So it's great because now closure construction is very cheap. It's essentially a no-op. There's nothing to construct, nothing to allocate. Everything is in the registers. Closure access, variable accesses are very cheap as well because there's nothing to load. Everything's in a register. So what's wrong with this? Number one thing that is problematic, well, not problematic, is maybe a concern of us, is that if now another function f closes over k, instead of just closing over k itself, now it has to close over the spread of k. Now it closes over 4 variables that used to be bound by k. So we basically move allocation from one place to the other, which may not be a smart choice always. And the second one you're probably thinking of right now is that by doing this rewrite, by spreading k across many variables, we change the calling conventions for id and k. So we have to make that consistent somehow, right? So we need to somehow find out all call sites that could possibly call id, and I need to find all functions that could possibly flow to k to update the calling conventions consistently. So calling convention must be consistent is sort of the main issue with this approach. But now we widen our permissive environment representation even more. Now the environment is just a graph with any number of roots. So that's our closure representation so far. And it must do so by consistently updating the calling conventions and consider the register pressure downstream. So that is the two optimization techniques that we like to do, and it's each with its own trade-offs. And the second half of this talk is going to talk about how we made those choices. And we focus specifically on what information we might need to know. So to make smart sharing decisions, we need to know a bunch of frequency questions. Is the functions defined more often or called more often, which means that should we optimize for closure creation, or should we optimize for a variable access? And for each variables, are they accessed often at all? For spreading optimization, we have sort of a related but different question, which is that what are all variables that could be bound to a function? And conversely, what are all functions that could be bound to a variable? And if you realize that one side of this question, the frequency question, is a question of control flow, and the other side of the question is the question of a data flow. And very fortunately, higher order flow analysis gives us both. It provides a sound over approximation over data flows and control flows. And for this, we designed an efficient, sparse zero CFA analysis in the compiler of CNML of New Jersey, and that works at a scale as well. And by sparse, it really means that unrestricting values such as integers are not tracked at all in this analysis. That gives us efficiency. At the core of this analysis is such a flow rule that says, in module M, U may flow to V. That is what that relation is saying. And this is defined recursively, and the analysis itself just computes the least fixed point of that relation, and then we know that this is sound because it's the fixed point already. So how do we use this? To answer the control flow question, from the control flow analysis, we derive the control flow graph, which tells us actually more than what a traditional intra-procedural control flow graph would do, because it actually tells you for a higher order function f in this filter function here, written in a very standard way, what f really is. If these are all I have in my program code, I know precisely f can either be even or odd. So from this, we can construct an approximate, what we call control flow graph, and then we can do a bunch of ordinary analyses on this, such as loop analysis and branch prediction, and we can answer the question that we're actually interested in. Is f called in a loop? Is f defined in a loop? Is a branch more likely to be taken than the other, et cetera, et cetera. And from then, we consume that result by performing a variable usage analysis that tells us how a variable is used, or a free variable specifically is used in a function. Are they used solely to create other closures? That means that it's a prime target for sharing. Are they used directly on the hot loop path, which means that it's a prime target for compaction? So on the flip side, on the data flow question, we perform what we call the closure class analysis. So this is the same example again, but now that we draw a bipartite graph as follows. We have definitions on one side. We have variable uses of a variable on the other side. We use defs use as the standard terminologies for data flow analysis. And we draw an arrow if a function could flow to a variable. Now, each connected component in this bipartite graph is a closure class, and closure calling conventions needs to only be made consistent within the class, but different classes can use different calling conventions. That gives us really granular yet sound control over the amount of spreading that we're allowed to do. So obviously, the next step is that once we know all the classes, we perform a spreading analysis that answers the questions of what the number of variables for each class is that we should spread to, and that is considering the available registers that this class appears everywhere in the program, and also the impact on other closures as we talked about. So once we have both sides of the equation, we can perform our layout decisions. We know a lot more about the program than we originally would without those analyses. So now that we actually make the actual layout decisions by performing a top-down greedy sort of traversal of the program text, and at the end we rewrite the program based on those layout decisions. We're very fond of this design because it separates very cleanly the analyses, which finds about facts about, of the program, and the decision, which are policies and heuristics, and the actual transformation. And all of these can be swapped out in our development process. Well, the obvious question is, does it work? But before we're talking about that, we need to talk about what is the baseline of comparison. So the baseline comparison is that the SMR New Jersey actually implements a very sophisticated closure conversion already without using a high-order flow analysis. That is the work done by Sheldon and Appel in the late 90s. And it performs closure sharing already, but they base on an imprecise syntactic control flow graph with a bunch of really fancy heuristics. Because they don't do closure class analysis, their spreading can only be confined to a global decision. In this case, they spread all continuation closures uniformly to use 3 extra variables. And they, obviously, for syntactically known functions, they use the custom calling convention for all of these because they're well known. So we implemented our methods on Standard New Jersey on 2025.2 with an LLVM backend. And we perform a direct comparison by swapping out only the closure conversion part while leaving everything else exactly the same. And we evaluated on both x86 and 64, x86 64 and ARM 64 architecture. And we focus on our results here today on ARM 64 because it has lots of free registers for us to spread to. And the runtime speed up is significant. And with our method, we achieve about a 10% speed up, the geometric mean across our benchmark suite. In the most extreme cases, we can actually speed up programs by 1.7x. And this drops the runtime from 10 seconds to roughly 5.8, a little bit more than 5.8 seconds. And similarly, we can achieve tremendous allocation savings. In some cases, we're only allocating 16% of the original program, which is, is pretty, in our opinion, is pretty substantial. And lastly, I want to point out some of the other work that relates to ours. First of all, is a defunctionalization question, which focuses on the representation of code part of the closure, while we focus on the environment part of the closure. Second of all is lightweight closure conversion, which focuses on the free variable sets that needs to be closed over. They try to reduce those while we basically keep everything intact, but only use try to represent those environments in a smart way. And lastly, we have unboxing and error erasing, which closure spreading is sort of an instance of. Right? The main takeaway is that better flow information can be used to make better closure representation decisions, as we've shown here. There's a lot more in the paper, and the artifacts are available. And with that, I'm happy to take questions.
Thank you, great talk. So I was wondering about the, you have to be consistent with the calling conventions if you start adding variables for your functions. Can't you do eta expansion to kind of fake that? So if you eta expand that and then you can fix the call sites.
Well, we can, yes. Well, the question is that can we use eta expansion to fix that issue? But then, that makes...
But you introduce a new function which still has
exactly.
the same issue,
we again move allocation from one place to the other.
But at least if you have a function which is used both in a known and unknown way,
yes,
then you can do the eta expansion to at least consistently optimize the known functions.
Yes, right? That's something that we already do by the compiler. Like, if a function escapes and also used internally, there will be a wrapper around it that allows you to customize the internal version, but sort of keep the external version sort of intact.
All right, thank you.
Mm-hmm.
Any other questions?
Thank you. You showed this an example of the closure overcapture, which you classified as a leak and inherently bad. But isn't that another dimension for optimization? If there is a price of memory, but there is also, you can reuse more of the structure if you overcapture.
Sorry, can you repeat the last part of the question?
Can you consider this another dimension for optimization? If you overcapture the closures, you can reuse more, but at the price of more memory use.
To some extent, we use that here in our compiler. So if we figure that C is actually an integer, say it cannot be a pointer pointing to a giant data structure, we implicitly allow this. And similarly, for this example, K1 subscript C, which is a code pointer, which is not free in anything else, but we consider that sort of not going to be changing the space complexity of our program. So we actually would point that pointer directly to K1's closure instead of being a separate tuple here. So, I mean, that really depends on what kind of guarantees that your compiler is supposed to give the user about the space safety. But yeah, definitely that is something that we do already.
Maybe we can take one more question if there was while the next speaker sets up.
Great talk. Have you considered using profile-guided optimization for this? Because it seems like if you can count how many times a function is created or called, then you can be very precise about how to represent your closure, or which one is better.
Yeah, definitely. Well, in coming up with the decisions, we actually inject a lot of instrumentation code in the generated code itself too. That allows us to validate whether the heuristic, the kind of decisions that we're making are sound or sort of like are making any progress or not. But yeah, definitely, with some setups, we can make it a profile-guided one, but that hasn't been done as we consider that as a future work.
Great, let's thank our speaker one more time. And then we'll go to the next talk, which will also deal with sort of doing something to deal with control flow conversion in higher order. And it's by Roland Lysa.
All right. All right, thank you very much. So let's jump straight into that. So this is joint collaboration with my student Johannes, who did all the lean proofs of that. And we all do know SSA form, and there's this classic dominance property that we all love and hate. So each use of a variable must be dominated by its definition, right? And dominance, this whole concept of dominance in SSA form underpins a wide array of analyses and transformation. But there's a catch. For dominance, it's derived from control flow. So we need this control flow graph, right? So if you don't have a control flow graph, it's kind of debatable what the dominance actually means. So this whole concept of dominance in SSA is only well defined for first order control flow graphs. So what do we do about higher order functions? So with this whole concept of dominance, there are two problems that I'm going to elaborate a little bit more in a minute. First of all, dominance is imprecise. And second, dominance is undefined for higher order code. So control flow over-approximates data flow, and I have this a little example here with two nested loops. Here's the dominator tree of this thing. And we have two nested loops. We have this outer loop with this header hi that introduces this induction variable I1. Then we have nested inside of that this inner loop with this header hj that has this induction variable j1. And let's say we want to do some kind of loop transformation. So let's say we want to, peel the outer loop. And in order to pull that off, we have to specialize this phi I1 and to specialize that to the first phi argument 0, right? Now, if we want to unroll the loop, we have to specialize this whole loop with the phi I1 using the second argument of the phi j2. Now, here's the problem. If we look at the dominator tree, we can see that the dominator tree tells us that the inner loop hj kind of hangs, has a dependency hi, so this outer loop. But as a matter of fact, this inner loop doesn't actually use anything that the outer loop is defining. So this dominator tree shows a false dependency. So in order to peel or unroll the loop, we don't actually have to touch the inner loop in this example. So here's problem 2. So let's say we are writing some kind of higher order program, such as we want to pass to a function eta some function f that we want to iterate. So we want that f0 of x is x, and f1 of x is f of x, and f2 of x is f of x, and so on and so forth. So we can easily write this down in a functional programming language such as OCaml. So here we have this function eta that takes this function f as an argument. Here we get the arguments n and x. And now what we can do with this eta function, for example, we can successively use this eta function with partial application to build addition, multiplication, power, and then compute 3 by the power of 5. Now, we don't have an explicit CFG here. We're passing around functions all over the place. So this property, every use must be dominated by its definition, kind of loses its meaning here, right? So we can only represent this program in SSA form in a control flow graph if we are going to lower that with some kind of closure conversion. And if we are down that rabbit hole, then the closure converted program looks really convoluted, and it's really difficult to reason about that and do any meaningful transformations in this state. Now, folks that are building compilers for function programming language, such as SMLNJ that we've seen in this talk earlier, so they're using as an IR something which is rooted in a lambda calculus, and they typically don't talk about dominance. What they are usually doing is they have a syntax tree, and we are just relating uses to the definitions just by the syntactic scoping of the program. However, the scoping is too rigid, right? So for example, let's say we have this function g of y that is nested inside of f of x here. But we can see that there's actually no reason for this function g to be nested inside of f, right? So this means if we naively beta reduce f, we would end up with a copy of g. So in order to fight that, we would first need some kind of phase that hoists g out of f. So usually it's called some kind of block floating, and then we are good. There's also some kind of the reverse problem. So let's say we have this function f of x of y, okay? Now we're seeing here's one call, fz1, and this other call, fz2. So we may come up with the idea to specialize f with z. But now we have to be super careful where we place this new specialization, because we're using this variable z here. So we actually have to make sure that this new specialized function that we're creating here is placed inside of g. Now, as a little recap of what we've talked so far, so for control flow graphs in SSA form, we have as a structural foundation dominance, and we're using basic blocks all over the place. We don't worry about syntactic scoping or anything like that, because this dominance property tells us whether the use of a variable is kind of makes sense. The downside of that is that we at least directly cannot support higher order functions. If we use some kind of variant of a lambda calculus, we have an explicit scope nesting, which means that we are not scopeless, so we constantly have to fight the scoping, but we do have support for higher order functions. Now in our work, we introduce this lambda graph, or lambda g, which is a lambda calculus, so it supports higher order function, but it's also scopeless, so all those functions are floating around just like basic blocks in a control flow graph. Now the question is, what kind of structural foundation do we use? So dominance is out of the window since we want to support higher order function. What we use instead is what we are calling free variable nesting. I will explain that later. But first, let's have a look how we can actually represent an SSA form program in lambda g. So we're using this correspondence between static single assignment form and continuation passing style to translate that. Here you can see the original SSA form program, and here you can see the program in lambda g. You can see that each and every basic block here becomes a little function, right? And all those functions here, they are just like basic blocks in a control flow graph. They are not nested inside of each other. They're just like a flat kind of structure. And each function has a label. Then we have a lambda, and then we have a list of parameters, there's only one variable. If we want to have more parameters, then we have to use a tuple. And in order to identify the variable, we use the same label as the function. We just put var in front of that. So var f0 means this thing, and var f1 means this thing. Since this is a continuation passing style where we are making the return continuation explicit, so here we have like just magically this return instruction there. But what we can see here, we are just using this red variable over here. And this is a major feature of lambda g, that we are just using this variable here that has been declared over here, just like we would do that in a CFG with basic blocks, but it's not nested. Another thing is what becomes with those phis here. So we can see, for example, here this loop header hy. This phi thing becomes a parameter of this function here. And this argument 0, we are passing that. So this goto just becomes a function call. And we are passing this argument as argument to this function. You can see how this plays out in this other recursive call where we are passing J2 to this loop header. Now, the cool thing is if we want to do some kind of loop transformation, such as loop peeling or loop unrolling, this just becomes beta reduction. So if we want to peel the outer loop, we just have to beta reduce HI0. If we want to unroll the loop, we just have to beta reduce HIJ2. Now the question is, we now have those soup of functions. How do we recover some kind of nesting for that, such that all variables are properly scoped? And first of all, if we have a function g that uses the variable introduced by f free, then obviously g must be nested inside of f. So if we would translate that to OCaml, we would see that g actually is nested inside of f such that it can make use of this variable over here. Nesting is transitive. So for example, here we have this function g that uses the variable of f. So f nests g, but h uses this variable g that g introduces, so g nests h. So this also means that f nests h, so nesting is transitive. Syntactically, we can write down nonsensical programs. For example, we can have a program f that uses the variable of g and a function g that uses the variable of f. And this is nonsense, right? We can't come up with some kind of scoping, nesting. We can't translate that to OCaml because we kind of have this contradiction here. And this is the nesting property. Nesting must be antisymmetric. And this replaces the classic SSA dominance property in our framework. And in fact, in the paper, we prove that if a lambda G program is well typed, and we have a situation where f nests g nests h, that this implies that g dominates h in the corresponding control flow graph. The reverse does not necessarily hold, so this means that nesting is more precise. Since free variables are all over the place, and parsers can mutate the IR freely and query free variables at any time, we have this incremental free variable analysis. So at any time, you can ask an expression or a function for its free variables, and they are lazily computed on demand. And once we have the result, they are cached and memorized per functions. And then when later on asked the same question, then we get the answer in constant time. If we mutate the IR, we have to invalidate the caches. This is also implemented quite cheaply by basically just bumping some integer. And this whole framework with free variables, you don't have to rescan globally. You don't have to do a manual reanalysis. You just ask for the free variables, and you get the answers transparently, as opposed to dominance information in SSA, where you change the CFG, and then you have to recompute the dominator tree, right? So here, you just ask for the free variables, and so you don't have to worry about that. Beta reduction in our framework uses this free variable analysis to pull that off. And in particular, we don't need any kind of block floating. We are only specializing expressions as needed. And the gist of it is that we maintain a set of variables that we want to substitute, and we skip substitution when the intersection of the free variables of the expression that we consider for substitution and the set of the variables that we want to substitute. If this intersection is empty, then we don't do anything about that and continue. All right, here's once again the double loop example. Here we can see the dominator tree. And based on this concept of free variables, we can derive a data structure that we call the nesting tree. And you can see the nesting tree correctly identifies that both loops kind of live side by side because they don't depend on each other, as opposed to what you see in the dominator tree. Once you have the nesting tree, you can translate this program into a explicitly scoped language, such as OCaml, what you can see here. And you can also see those dotted lines. These are the dependencies of the functions at the same level, which basically tells us in which order we have to place those local functions in our OCaml program. Those dependencies might be cyclic, which means that we have to use letrec. Here we change the program slightly, And this time around, the inner loop actually does depend on the outer loop. You can see that the nesting tree changes and mirrors this. Almost looks like the dominator tree, with one exception. This is just how the free variables play out. But lambda G is not only limited to continuation passing style. It doesn't care whether you want to use CPS or direct style. So back to our example with this eta thing, we can translate that to lambda G in a straightforward manner. And here you can see the forest of nesting trees, how this can be computed without any form of control flow or dominance whatsoever. We evaluated that in our research compiler Mimia, which generalizes these concepts that I talked about for dependent types and other binders. So for example, if you have a dependent tuple type, this is also just a binder like a function, and those concepts work for those things just as well. And for all those things, computing free variables, beta reduction, or computing this nesting tree, we have n-log-n scaling using our data structures. Only for very pathological cases, if you have hundreds of deeply nested loops, the performance degrades. But this doesn't really happen in practice. So for example, in the whole SPAC 2006 benchmark, the max loop level is 22. So here you can see how different concepts map to lambda G from CFG with SSA form. So we've already discussed that both functions and basic blocks are just functions in lambda G. Function parameters, phi functions, are lambda variables. Function calls and jumps are just applications. Function call arguments or arguments to phi functions are arguments to this application. All those things such as function inlining, loop healing, loop unrolling, or any kind of CFG specializations are beta reduction. We talked about this SSA dominance property is now superseded by this nesting property. The concept of dominance kind of mirrors free variables. The dominator tree, if you need that, you can compute the nesting tree instead. There are some extensions to this dominator tree, such as a DJ graph, or if you're looking at the whole program, you typically complete a call graph. You can all do that with a nesting tree. And if you look at the sibling dependencies and compute this, then this kind of maps to a loop tree or call graph with STCs. Directly recursive function or natural loops map to direct recursion in lambda G, mutual recursive function or irreducible loops map to mutual recursion in lambda G. Also another thing, critical edge elimination kind of generalizes to eta expansion. Didn't have time to talk about that, more on that in the paper. So the takeaway is that nesting is a relaxed form of dominance, and we replace control flow dominance with a data flow notion of nesting built on free variables. It's more precise because it directly tracks data dependencies and not control flow. It supports higher order, well-defined where dominance is not, and it's practical. We have this incremental free variable analysis where we're caching the results, log linear in practice, and constant time access if those analysis information is already in the cache. So thank you very much.
Thank you, it's very interesting. So you mentioned theorem there about nesting and dominance. Have you proven it? And if yes, if it's paper proof or mechanized proof?
So we've proven that nesting implies dominance, but not the other way around. So I didn't caught the second part of your question. What was it?
If the proof is paper proof or mechanized proof?
It's mechanized proof. We've done that in Lean.
Hello. So I have a question relating this work to what MLIR is doing these days. So the MLIR these days have like basic blocks with arguments inside, and those have kind of replaced the traditional phi nodes. Is this something similar? Because it seems very similar to me.
Not really. So in MLIR, they're using block arguments, which kind of plays in this whole story, SSA, CPS. But other than that, MLIR is not really a higher order representation. They do have those regions, but once they have those regions, they kind of going this nesting route, what you do with a typical lambda calculus. And then inside of those regions, they're computing a dominance tree, and then it kind of directly hangs in the dominance tree of its parent scope, but it's also an over-approximation, because it might be the case that the region in MLIR doesn't have any free variables at all, so it really should sit right at the top, but it's not, it's just sitting there. So I hope this answers your question.
Okay, one more while the next speaker sets up.
Just wondering if there's anything to do with the Brownian index, since it's something like SSA for the lambda calculus, and a greater index may imply dominance.
Sorry, I didn't understand your question. So you're talking about de Bruijn indices and how, so I mean, in the end of the day, it's a matter of how exactly you want to represent your variables. So we, in the end of the day, have a named representation, but you could totally apply that with de Bruijn indices. It's just that we are also working with a mutable representation, which rules out many of the more other fancy representation to represent names. And the other thing is that with de Bruijn indices, because we're doing aggressive hash counting, you're getting both false positive and false negatives. So de Bruijn indices isn't really anything that we want to do in our representation. But I can imagine that if you're doing a different compiler design, then this should probably work out for you. All right.
And the next speaker will be Han Nguyen talking about static analysis on binaries the moment we get the slides up.
So first we want to talk about what is the problem we're trying to solve, and what is the solution that it looks like that we're trying to achieve. And the next we dive deeper into the background, like what is the challenge in the assembly, why we have to do it binary analysis without the assembly, and what is the challenge in doing without the assembly anyway. And we show that we can do it. We can ship that because of one key insight. And then we apply that key insight into doing more binary analysis if we have time. And then finally we evaluate our accuracy and scalability compared to state-of-the-art binary analysis tools. So I give you one example of real world. Since today real world we have a lot of memory vulnerabilities, right? You give a program, and that program has vulnerabilities. And the attacker can feed malicious input into it, and then it leads into sensitive information leakage or arbitrary code execution. For example, root privilege escalation. So the first step of a hacker has to do is to first reverse engineering the binary code 0101 into some memory layout that they can understand and analyze the vulnerabilities. So reverse engineering has a lot of applications. Maybe the most famous one is security, but it also is important in software corrections, profilings, optimizations, and also protection of intellectual properties for industry companies. So what is the step, the workflow in the reverse engineering? First, you have the binary. Then the first step is you have to disassemble into assembly. Then you apply binary analysis on top of assembly. Then you achieve your goals. So the thing is that disassembly itself is very hard. So typically you need something to support, to assist, to guide the disassembly to be more accurate. So this creates a chicken and egg problem. Like you need disassembly to do binary analysis, and then you need binary analysis to make the disassembly more accurate. So what is the problem of this one? Is twofold. So the first problem is scalabilities. So because there are many analyses has to be doing repeatedly until we convergence. And so that it leads to quadratic complexities. Put in terms of practicals, right? Runtime complexity, it takes for Angers and Ghidra maybe like a half day or more than a day for 1 gigabyte of total size of binaries. In terms of memory, it look even worse. Like you see that only to analyze 10 megabyte binaries, it takes Ghidra and Anger 5 gigabyte RAM, and for some tools like that already assembly, it takes 60 gigabyte RAMs. So remind you that, for example, Firefox share library, one share library of Firefox is 250 megabytes, and this year we are talking about 10 megabytes. So this is the scalability issue. In terms of accuracy, so right now binary analysis accuracy is bounded by the disassembly accuracy, because we do the disassembly first. If we get a wrong disassembly, we get a wrong binary analysis. So the state-of-the-art disassembler try to cope with it by doing some conflict resolution, but conflict resolution itself is error-prone. So this have some hint for what we want to achieve. So we want to achieve linear time complexities. So that means that we have to analyze each instruction exactly once. We don't have time to do it repeatedly, and we have to compute a constant amount of information, constant amount of time for each instruction. In terms of accuracy, because we want to not be bounded by disassembly accuracy, so now we have to completely avoid disassembly at all. So that means that because we don't have disassembly right now, every possible byte offset in the binary could be a valid instruction. So that means that we have to analyze every possible byte offset. This could prove to be useful for improving accuracy of own disassembler, because regardless of disassembler, we provide every information. In terms of the accuracy, we want to achieve all of what we just said, but without sacrificing the accuracy. We want the best compared to the best state-of-the-art tools. So visualize, right? So this is what we want to do. Instead of replacing the binary analysis, we don't. You can keep using the binary analysis that you are using, but we try to proposing a new binary analysis put right before disassembly. So we analyze direct byte, and we provide useful information to improve the disassembly. So now I'm talking more about the background. So I talk a lot about disassembly is challenging, but what is the challenge? That fundamentally disassembly is about distinguish code and data, right? In the more complex program like Firefox and Chrome, you will see data embedded in the code segments. So you look at 0 and 1, you don't know what is code, what is data. So that is real for example, the case of jump tables, for the case of handwritten assembly, or little pools in ARM64 architecture. And existing tools, because of this challenge, so existing tools suffer to 15% of the assembly error rate. This is also because of a few reasons. I can name some fields like complex instruction set like x86. Any instruction, any random byte sequence, you from 1 byte to 15 bytes, looks like you can decode it into a valid instruction. So how you can distinguish the valid code or data? So the next one is compiler metadata can be useful for reverse engineering, but it's completely absent in the production binaries, like symbol information, debug information, exception handling information. Last one is the unreliable code patterns, like some
techniques, binary analysis techniques rely on those, but these are very fragile because it depends on the compiler optimization. So now because of this challenge, we want to use binary analysis to tackle down this problem, like separate data from code. And remind that we just said that looking at the byte sequence, we don't know whether it's a code or data because almost every byte sequence can be decoded into valid instruction. So now we are looking more into the path properties. So path property, like you're looking into like a sequence of instruction execute, and then we tell something, okay, maybe this is not code, maybe this is not data. So for example, we name here 3 examples. So stack depth and register preservation and initialize values. So for example, stack depth, right? So when you execute a function, you want, after you execute a function, the stack pointer should restore to be the same at the beginning. So the property we want to compute here is the change in the stack pointers between 2 different points, param points. So we want to say that the stack pointer at the beginning of function and at the end should be the same, 0 change. So for example, the register preservation, when you have 2 binary code, you want those 2 binary code compiled by different compilers. How they can communicate to each other? They have to accept to a common rules, and that common rule is application binary interface. And for example, that one dictates that some register, x86 register, need to be preserved into the stack at the beginning of function and then restore at the end. So what we want to compute here is what is the stack location we want to save from and restore to, restore from and save to. I will skip the last one because of time limit. So now we understand that how we can do binary analysis to help the disassembly. Now, what about we don't have disassembly to begin with? What is the challenge of doing that? Every byte offset is a potential instruction. Like as I said before, because we don't have disassembly, every byte offset is a potential instruction. Then the first problem is that the analysis, the results at the intended instruction is polluted by unintended instruction. For example, right? You look at this one. The 2 blue one is a valid instruction. 2 instruction will be executed at runtime. So the first one is decoding to a compare. The second one is conditional jump. But if you see that one, right? This one is also like a valid encoding instruction. So now the second instruction, the 74 for the second blue one, right? They have 2 predecessors. One is the blue one, another is the yellow one. So when we do static analysis, we want to do it in linear time. We have to merge. We have to make approximations, and because we have some bogus edge, so it will reduce the precision into what is being useless. So that's the first problem. The second problem is that we are talking about path properties. And now, without this, we don't even have the beginning point, right? Every point could be a beginning point. Every instruction, every byte offset could be a beginning point. So that suggests us that maybe we should looking for the other approach. We should looking at the ending point, starting the analysis from the ending point rather than the beginning point. So there are some ending point very popular. I will talk in more detail if I have time, but essentially we want to do backward analysis instead of forward analysis. And the last one is linear time complexities. So because of this constraint, so the property we are looking for is the path properties that where, across different ending point, it should be the same. So what is the example of that is the 3 examples I just tell you. So regardless of, you exit in this function in this way or that way, the property must be the same for function properties. So when I say analyzing byte, what does it look? So I just want to give a brief look at that. So the right-hand side is the column is the assembly language of x86. This is the column of hexacode, and then the left one is the column of instruction address. So the dark line is the intended instruction, is a true instruction, will be executed at runtime. On the rest is not the true instruction. So we want to find the black line. And for example, this is how we do it in stack depth, right? So this is just the same example, but we simplify, we remove something out of that. So the arrows here, just that after you execute that instruction, it will be, do I have the mouse here? I don't. After you execute that instruction, you will flow into the next instruction. So on the right-hand side here is the stack depth, the change of the stack pointers from the ending point into the beginning into that instruction. So there's two ending point here, right? It's a return instruction, red instruction here, red instruction there. So if any instruction that can reach that red, the below red, it will be the blue line. If any instruction that can reach the other red, it will be the red line. I think that color is red. The pink color is about obviously non-instruction. We don't need to care. So you see at the 29D44, that would be a white color line. So that one is actually a merging of two branches. So the branch, the blue line and the red line merge each other at that line. So it has the color of white. So then you see that at the beginning, right? The first instruction, the stack depth is 0. So now you can say that because stack depth is 0, this is very likely to be a function entry. So we can still doing stack depth analysis even in even without the disassembly. So why and how we can do it? That's because the very important key inside of that this one we call it backward path fidelities. So to understand this, you have to compare forward and backward data flow. So for example, in the forward data flow, right, true instruction always flow into true instruction, but wrong instruction, non-instruction can flow to true instruction or non-instruction, as we said before. Now, when we're looking at the backward directions, then we just reverse the arrow directions, right? Then what you see, the difference here is that right now, the true instruction cannot be preceded by a non-instruction. If you look at the second line in the forward data flow, right? True instruction is preceded by non-instruction. But if you look at the backward flow, there's no. True instruction can only be preceded by true instruction. So if we start from the true instruction, we can only reach true instruction. True instruction will not be polluted by non-instruction. So that means that we can separate the two, instruction and non-instruction, separate them, the effect of them separate away. Without knowing what is an instruction and what is non-instruction, we can have some exception on that, but like we will discuss later. How many times is it? 3. So I will try. So in these properties, we want to make sure that the register R is safe and preserved at the same location in on path. So what we mean is that the SB restore is the stack pointer at the restore of the register R, and we want them to be the same. So SB this minus SB that will be 0. So we want to compute SB minus SBX. So fundamentally, I don't think I have time to explain this one, but I will move on. So now we come to evaluation. We will compare our accuracies between a backward analysis and forward analysis, and our analysis and state-of-the-art tools, including Angers, Ghidra, Dynix, Nucleus. Then we talk about scalabilities, linear time complexities, and performance comparisons. That data set that we are testing is, a famous one, Peng et al. In honor disassembly related papers, and the stuff was from Google. So now, first we evaluate compare the forward and backward analysis. So we see that we reduce false positive and false negative across all different properties, with the exception only this one, raising a little bit here. But other than that, we reduce false positive and false negative significantly across all different properties. Now comparing to the state-of-the-art tools, depends on how you do the macro average. If you do macro average, we are like a little bit behind Nucleus. But if you do micro average, we are even ahead of them. So in terms of linear scalabilities, to analyze 300,000 byte offset, it takes only 1 minute, and it takes 2 GB of memories. How it's translating to, compared with the other tools. So you see that, for example, Dynix and Nucleus is very special, but Dynix don't do a lot of analysis. Anger and Ghidra do some heavy analysis, and then they take much longer time than our work on Amaze. So the peak memory, what I want to mention here is that Amaze analyzing own by offset. The other tools only analyze a subset because they use heuristic to prove now. The last one here is that we speed it up by about 700 to up to 1,000 times compared to forward analysis. So do we have time? Okay. So I will skip this one. So I come to conclusion. This is the first work. This is the first work on doing static boundary analysis without disassembly. We leverage a key insight on the backward path fidelities and to do backward analysis on a superset control flow graph. And we provide results at every biopsy. We shall achieve linear time complexities order of magnitudes faster than the others, and without using heuristic to prune possibilities. And we achieve the same accuracy to the best tools. I also have some link here for you to try out our tools. Thank you very much.
Very nice. I think we have time for about one question while the next speaker sets up. I'll ask one. So you had accuracy about the same as existing tools like Ghidra. Are the sources of the inaccuracies the same between your tool and others?
So
Ghidra,
it must be high. The one that comparable to us is an academic tools. So that is. So what is your question? Why Ghidra is worse?
Are the sources of you had accuracy comparable to other tools? Are the sources of inaccuracies the same or different?
Okay, so this is hard to break down, but like most of the tools, they make assumption. They make some assumption. For example, Nucleus make some assumption on, control flow graph must be, is fine if, we don't have a repeated, a big loop in the function. They make some assumption. But basically, for example, Nucleus, they have to rely on linear disassembly. They have strict linear disassembly requirements. The other tools don't have, but they do some heuristic, like, okay, this is too hard, this take a lot of time, they prune it out. So different tools have a different way to compromise on the results. But to our surprise, Nucleus is decent, even though it's simple. Yeah, okay.
Thank you. Thank the speaker one more time.
Okay.
Okay, so we heard about static analysis of software and of binaries, and now we'll hear about static analysis for hardware. Description languages like Verilog. And the speaker is Jatsai Sui. Take it away, please.
Thank you very much. Let me take a deep breath. Hello, everyone. I'm Jiacai Cui from Nanjing University. I'm a second-year PhD student advised by Yue Li, who co-runs the Pascal research group with Tian Tan. Today, I'll try my best to present this work on behalf of the first author, Qinling Chen, who was unable to attend due to visa issues. Our paper is titled Exploiting Sophisticated Static Analysis for Verilog, the prominent hardware description language. In this talk, I'll first discuss the untapped potential of hardware static analysis, and then I will introduce Qi, the first general-purpose static analysis framework for Verilog. After that, I will show what hardware static analysis looks like in practice. Finally, I will present our preliminary experimental results on applying hardware static analysis to diverse application domains. Let's start by talking about why we want to do static analysis for hardware. If we look back at how static analysis has evolved in the software world, we can observe a large amount of untapped potential of static analysis in the hardware world. In many ways, hardware development resembles software development. Hardware is programmed in languages like Verilog, and its quality is ensured through techniques such as simulation-based testing and formal verification. Sorry, I cannot find my curses. As for, okay, I have found. Oh, it's on the other screen. Okay. Oh, I found that. Sorry. However, as of 2026, static analysis in hardware is still underutilized. The overwhelmingly dominant hardware static analyzers are linters that provide basic syntactic checks, such as naming conventions, style rules, and simple pattern matching. This is similar to software in the early 2000s. At that time, standalone software static analyzers largely meant linters as well. However, over time, as software become more complex and more diverse, static analysis has evolved significantly significantly, thousands of analyses emerged for bug detection, security assessment, and program understanding. These are sophisticated semantic analyses beyond linting that reason about program logic, properties, and intention. They have led to widely used tools like cloud static analyzer, covariety, PTANT, and many other tools. Now, if we turn back to hardware, we are seeing a similar inflection point. Hardware designs are also becoming more complex and more diverse. We are seeing many domain-specific hardware accelerators emerging for areas like AI, graphics, bioinformatics, and so on. We believe static analysis in the hardware world could likewise evolve into sophisticated semantic analyses that help detect hardware bugs, improve hardware security, and deepen our understanding of hardware designs. And today, this area is still underexplored. Therefore, to support the exploration and exploitation of hardware static analysis, we developed Qihhe, the first general-purpose static analysis framework for Verilog. Qihhe was a challenging effort. We spent 4 years developing it from scratch, drawing on our sustained communication with industrial hardware practitioners, with an in-depth understanding of formal Verilog semantics, and our decade-long experience in fundamental static analysis research. Now it has grown to over 100,000 lines of open source code, and I'll introduce it for you. This is an overview of Qihhe. It summarizes its main components: the front end, the IR intermediate representation, the analysis manager, the general purpose fundamental analysis, and the application specific analysis. Although Qihhe is a static analysis framework, our goal is to enable real-world adoption of sophisticated hardware static analysis beyond the linting. Therefore, Qihhe comes with a set of out-of-the-box built-in application clients as demos of its capabilities. These analyses are motivated by the needs we gathered from both hardware literature and our communication with industrial practitioners. And they span diverse areas as mentioned before. As a framework, Qihhe's most important component is its fundamental analysis. These analyses are designed to be reusable building blocks for diverse application-specific analysis. On average, each fundamental analysis is already reused by about 10 built-in application-specific analyses in Qihhe. These fundamental analyses address essential hardware characteristics that handle Verilog's 4-valued bit vector semantics, capture how synchronization and concurrency work in Verilog. They also support analyzing complex hardware control and data flows. The remaining part of Qihhe is its infrastructure. We provide an analysis-oriented front-end and IR for Verilog. It also supports analysis of incomplete hardware programs because in hardware practice, encrypted IP cores are common and their Verilog code is typically not available. In addition, we provide a user-friendly analysis manager that simplifies analysis development. We hope our framework can make life easier for both Verilog analysis users and future Verilog analysis developers. If you are interested in developing analysis for Verilog for hardware, you may wonder these questions about hardware analysis problems, insights, and challenges. To concretely answer them within a short time frame, I'll use a motivated example, missing reset analysis. It has a closed software analog used before initialization, or UBI. In both cases, an undefined value can propagate throughout the program and cause serious consequences. Since you may not be familiar with Verilog, I'll briefly give some background. Let's start with how Verilog code models hardware registers. Registers are a common hardware concept. They store values that represent the current circuit state and update on clock age. Here's a simple example of a register that accumulates input values on each clock age. The first line declares a register ACK, which is an accumulator. Line 2 declares 2 wires in, which carries the external input values, and the clock signal that toggles between 0 and 1. Lines 3 and 4 specify an OS block, which says whenever the clock transitions from 0 to 1, which is called a positive age, as specified by this POSH keyword, ACK is updated to its current value plus the input value in the current cycle. However, when a circuit powers up, registers start in an undefined state. To address these, hardware designers typically include a reset signal that users can assert to trigger the reset logic, forcing registers into a predefined known state. In this example, a new input via reset is added in line 3. Inside the always block, a reset case is also added. If reset is asserted, ACK is set to 0 as its initial state. Otherwise, accumulation update is performed as before. The table on the right shows how the value of ACK changes over time. The first column shows clock cycles. Each line corresponds to a clock cycle where clock toggles between 0 and 1. The second column shows how the input value changes at each clock cycle. In cycle 0, ACK is defined. ACK is undefined because the circuit has just powered up. Then line 5 is executed as triggered by this positive clock edge. Since reset is 1 in this cycle, line 6 executes and sets ACK to 0 for cycle 1, not for cycle 0, for cycle 1. This is a special semantic of this left arrow assigning operator, which is called non-blocking assignment in Verilog. In cycle 1, reset is 0, so line 8 executes. Because in S2, ACK will take the value 2 in the next cycle. 2 plus 0 gives us 2. Similarly, in cycle 2, we can compute that ACK becomes 5 in cycle 3 in a similar way. With this background, we define the missing reset problem. A register has the missing reset problem if its undefined value is used infinitely often after reset. The key here is infinitely often. In contrast, undefined values being used only finitely often is typically acceptable because in hardware, unlike in software, defined values can take time to propagate through the circuit, especially in pipeline designs. Here is a simplified pipeline that propagates values from register X to Y and then to Z. During its execution, we can see that after reset, X becomes 1, and its value is propagated to Y and Z cycle by cycle. So these registers are eventually defined, which is good. Here is an example of the infinitely often case. Even though X is reset to 1 initially, in subsequent cycles, the undefined values in Y propagates to X and then feeds back to Y. This happens repeatedly, so the undefined value keeps circulating infinitely, which is a bad case. The missing reset problem may look similar to the UBI problem in software. However, they are fundamentally different. UBI flags a variable if its undefined value is used once in any possible software execution. However, in contrast, the missing reset occurs when a register's undefined value is infinitely often used after reset. Therefore, addressing missing reset requires hardware-specific insights rather than directly reusing approaches designed for UBI. To solve this problem with static analysis, our key insight is that only non-reset registers involved in circular dependencies can have missing reset problems. Here is the previous problematic example. This is its hardware dependency graph, which encodes all the dependencies in the design, like synchronization, reset, data, and control. From the graph, we can see that X and Y form a circular data control dependency. However, register Y is not reset, so it has the missing reset problem according to our insight. For the sake of time, I will leave Sauna's argument of this example analysis to the paper. After getting at least a sense of the missing reset problem and analysis, we can now talk about the challenges. What challenges arise in building a missing reset analysis? First, we need to understand how Verilog variables map to physical registers, clocks, and resets, since the problem is defined on top of these concepts. Traditionally, this information is not available until after the lengthy hardware synthesis process. Invoking a synthesizer to obtain it can take over an hour for a million-line design. In contrast, Qi provides analysis that approximates this post-synthesis information in just 3 seconds with high precision and recall. In addition, we need hardware data flow and control flow analysis to construct the graph structures we need for the missing reset analysis. To understand how variables are mapped to registers and clocks, we also need analysis for capturing Verilog synchronization characteristics. To enable more precise intermodal reasoning, we also need module hierarchy analysis and other supporting analysis. In summary, building a sophisticated Verilog analysis beyond the linting does require a substantial foundation, which is exactly why we provide Qihhe. Qihhe provides all of these supporting analyses and even more to be reused across a wide range of clients. This is a whole picture of Qihhe's analysis suite. Missing reset is just one small bug detection client among them. The nodes on the left are the fundamental analyses, and the nodes on the right are application-specific analyses. The edges indicate analysis dependency relations. We omit the edges between fundamental and application-specific analysis because the diagram would otherwise look cluttered. As mentioned before, each fundamental analysis is reused by about 10 application-specific analyses, which is why we call them general purpose. We call them fundamental. Finally, let's look at some preliminary experimental results of Qihhe's application-specific analysis. On hardware bug detection, unlike software, hardware tends to contain fewer but harder to detect bugs. That's because hardware designs typically undergo extensive simulation and rigorous verification, as hardware defects are too expensive to fix if escaped into production. Unlike software, you can deliver a patch over the internet. You cannot deliver a hardware over the internet. Even so, our analysis detected 18 bugs in 8 categories across hardware projects averaging 1.5 thousand GitHub stars. Half of these bugs were previously unknown, and all of them have been confirmed by the developers. Moreover, all of these bugs are beyond the capabilities of existing linting tools. On hardware security analysis, our Verilog taint analysis can find 15 information leaks from the well-known Trust Hub benchmark. Qihhe can also detect a class of hardware Trojan that exploit Verilog's special X-value semantics to hide their malicious behavior. On hardware program understanding, we evaluate Qihhe on 3 representative tasks: inferring clock signals, reset signals, and registers, and achieve 97% precision and recall on average. On hardware code optimization, we can identify a lot of useless signals that can be safely removed. Overall, these preliminary results demonstrate strong potential of hardware static analysis. With Qihhe's underlying framework support, the implementation effort of this application-specific analysis is also modest. Each client just takes about 300 lines of code on average. However, without Qihhe, building an application-specific analysis would require re-implementing all the prerequisite analysis from scratch. Our estimate is that this would take roughly about 20 times more code. In addition, our static analysis are also lightweight, even on a real-world code base with over 1 million lines of code. Running all of our 40 analyses here takes about 6 minutes in total. 6 minutes in total for a 1 million-line code base. Okay. There's one last thing I would like to share. Since its release 4 months ago, Qihhe has also attracted registered users from nearly 50 institutions across the world. And we welcome everyone to visit our website to access full source code of Qihhe. We also provide extensive documentation to help you get started with Qihhe and develop a new analysis. In addition, we offer detailed API references. If you have any questions or would like to discuss ideas, feel free to contact us. Thanks for your attention. Oh, sorry. This is our website and open source code, documentation, and API reference. For example, missing.
I think we're.
Okay.
So you emphasize case studies. Finding, but not verification. Is the analysis framework sound in general?
For fundamental analysis, we try to keep them as sound as possible for it to be reusable across many clients. For application-specific analysis, considering some practical usage experience, we would do more aggressive optimizations to reduce false positives. Therefore, we may sacrifice some soundness in application-specific analysis, but the fundamental analysis are sound. Yeah.
Well, you said as sound as possible. What does that mean?
Theoretically it's sound, but we cannot ensure there's no bugs in implementation, right? Yeah.
I see. Got it. Thank you.
Thank you for your question.
A very nice talk and impactful work. I have two questions. The first question is that you find some bugs and how you report this bug to the developers. Do you need to give some kind of input to help them diagnose the issue? And the second problem is that because you listed many different kind of bug types, so what's the expressiveness of this framework? So because, for example, can you handle some bugs that cannot be expressed by the data flow properties? Thank you.
For the first question, we report bugs to developers through GitHub issues or pull request if we happen to find a patch to the bug. This is how we report bugs. And for the second question, not all bugs here are data flow related. For example, for data log analysis, it's not a data flow problem, actually.
Okay, thank you for your answer.
Thank you for your question.
Thanks for the talk. This is really cool. Have you seen anybody build any analyses for like questions of physical design, like finding long timing paths or anything like that?
For Verilog static analysis, we have only seen linter-like analyzers. For some backend tasks, such like static analysis or static timing analysis, to find the longest critical path in the circuit design, so they can optimize performance. We have seen some work on that, but that's not from the language level. That's from the netlist physical level. Yeah.
Great. Thank you.
Could I implement sort of static analysis to find timing bugs using what Qi provides?
Actually, you can find critical paths in the source level, but hardware synthesizers do many things during synthesis. So I suppose not, because the physical latency, which is affected by voltage or temperature, those parameters are only available after hardware synthesis. In the source language level, you don't have parameters about physical cell delay. Yeah.
All right. Well, if there's no more questions, I'll thank the speaker one more time. And that's actually the last paper for this session. It was only 4.
All right, thank you everyone. Welcome to the type system session. So our first talk is from Kyang Cheng on the PREST system for programming language for randomized distributed computing. Take it away.
Yeah, so thanks for attending my talk. This work was done in collaboration with Professors Ankush Das and Marco Garboardi during my PhD at Boston University. So we developed this PREST language for writing and verifying randomized distributed programs. So just a very brief background. So scaling with distributed computing is very powerful, but it's also very hard. We have a whole slew of different kinds of bugs, like malformed data, deadlocks, race conditions, and lossy networks, and just all sorts of normal bugs that skip past us, our human auditing. And a lot of these bugs tend to slip past testing and make it into production. So randomized distributed algorithms can help combat some of these problems. For instance, for the very classical deadlock problem of Chinese philosophers, there's a elegant solution of doing it through randomization. For race conditions, there's various kinds of randomized leader election. And then for lossy networks, we have lots of retransmission protocols like the classical TCP. So randomized distributed algorithms are powerful, but they're also very hard to get right. So it is very hard to trigger and reproduce bugs caused by these things. So this can lead to silent errors, and where programs never crash, but might produce wrong distribution of outputs. And this can lead to very insidious privacy and security risks. So for instance, in the crowd forwarding protocol, which does a bunch of forwarding to anonymize a message, if our forwarding target is not uniformly randomly chosen, then an adversary might gain some advantage and then figure out who it was from, and that will kill our privacy. And this is what led to us to develop the PREST language. So PREST, which stands for Probabilistic Refinement Session Types, it allows for the embedding of probabilistic protocols into types. It has a message passing based form of concurrency and has a probabilistic semantics. And more importantly, it formally guarantees that the runtime behavior of our probabilistic programs actually matches their protocols. So I do want to clarify that this programming language is not a probabilistic programming language in the sense that we don't do inference. The type system more acts kind of like a lightweight program logic that ensures the correctness of our programs. Okay, so what we do is that the PREST language extends the probabilistic session types of Ankush Das, which was published at POPL. So here we have probably the most simple probabilistic session type that we can have, and it's a probabilistic bool type. So intuitively, this bool, as a channel or a communication channel with this type bool, will have the message true with probability 0.6, or it will have the message of false with probability 0.4. So this type acts as a contract between our senders and receivers. So for our senders, it has access to its own sources of randomization, and it must provably produce a message of either true with 0.6 probability or false with 0.4. And on the other hand, for our receiver, which is receiving this probabilistic bool, it can now rely on this randomness, true and false, as a source of its randomness to generate new probabilistic messages. So the paper of Ankush, so the original probabilistic session type paper already shown that if we only care about a fixed number of participants and a fixed number or fixed probabilities, that it's already very powerful and is able to express a lot of these protocols. However, the restriction of these standard probabilistic session types to concrete probabilities limits its expressiveness in many real-life protocols, which are often parameterized by probabilities or the number of participants. So importantly, PRESS generalizes these concrete probabilities to symbolic ones. And that does it through probabilistic refinement session types. So here, we have the new p-bool type, and now it's indexed by a logical variable p, which ranges over real numbers. And we can define it to be in the range of 0 to 1, so making it a valid probability. Now, if we case on this true now, this is intuitively saying that we're going to send or receive a true with probability p and false with 1 minus p. And during type checking, we'll emit a bunch of constraints that says, okay, p has to be a correct probability. Okay, so now we have our types. We also need a primitive source of randomness. So PRESS features this flip primitive for generating randomness, and it's very simple. So it just takes in an argument p, and it flips a coin. If it's heads, it hits heads with probability p, or tails with 1 minus p. So given p in 0 to 1, flip lands on heads with probability p, tails with 1 minus p. So now to type check a pressed process, the flip construct will actually interact with these probabilistic refinements. So here we are trying to implement a probabilistic channel using a flip to generate the messages. So here we have a make p-bool function where we are indexing with p, and it's in the range, the correct range to make it a probability. And then we are emitting on this channel C a probabilistic bool with exactly probability p of landing on true. So we're doing this through the flip primitive. We're flipping a coin, and if it's landing on heads, we're going to send on this channel C the true message. Otherwise, we're going to send false. So the way that we do type checking is that we would actually isolate one of these branches and look at it by itself. So if we don't care about the outer program and we just look at this channel C.true, so this is sending true on this channel C, then the distribution of messages that we could observe if we were the receiver would just be true at probability 1 and false at probability 0, right? Because we're never sending this false message, so it has to always be true. And similarly, for the tails branch, because we're only ever sending the message false, then we would have the distribution of true at 0 and false at 1. However, because both of these actions are inside of the arms of the flip expression, to compute the joint distribution of these two actions, we would have to perform a weighted sum of these. So the overall probability distribution that we would observe from this flip expression would actually just be the weighted sum of these, which is true at p and false at 1 minus p. So what our type checker then does is that we will synthesize a big SMT formula that constrains that, okay, the thing that we are going to observe on this flip, the distribution we're going to observe, actually matches the contract of the type. Okay, so now we've seen the basics of using PREST. I want to talk about modeling probability distributions in PREST. So many randomized distributed protocols require sampling from probability distributions. For example, in leader election, we have to sample from a bunch of candidates. In crowd forwarding, we have to uniformly sample from a big number of crowds, or big number of crowd participants. And in zeroconf, we have to uniformly sample from a IP address space. So how can we accurately state this through our protocols? So it seems we have a conundrum when we are faced with these sort of parameterized protocols, that we have to somehow encode a parameterized distribution like uniform 0 to k. And it seems that we are doomed to extend our language with some n-ary primitive, which will actually dramatically complicate the underlying theory. And this is because, so our flip only has 2 branches, and our probabilistic types have only a fixed number of branches. So how do we resolve this? So it's very fortunate that the parameterization actually saves us from this. So the key idea is to let probabilities and refinements interact with each other. So here we have a UNAT encoding, so UNAT as in uniform net. So intuitively it is trying to model a natural number uniformly sampled from the uniform distribution 0 to n. So this is a unary encoding of a natural number using session types. So the idea is that we're going to send a number of successor messages, and that number of successor messages will be the encoded number. The important thing to notice in this UNAT encoding is that the probability of us sending successor or 0 is actually controlled by the logical parameter on the type. So the successor has probability n over n plus 1, and 0 has 1 over n plus 1. And this will actually change as we start to unfold this UNAT type into a big trace of successor messages. So to see how this works, let's actually unpack a concrete instantiation of this. So let's say UNAT 3. So we would observe the 0 message, or just a single 0 on this 0 message on this channel. And this gets out with probability 1 over 4, because if we substitute 3 into 3 for n, we have 0, 1 over 3 plus 1, which is 1 over 4. And we would have the message trace suck with 0, which is encoding 1, with probability 3 over 4 times 1 over 3. This gives us 1 over 4. For suck 0, which is 2, we would have a similar expansion. That gives us 1 over 4. And then finally, for 4, we also have 1 over 4. So now we've seen, for at least a concrete example, that UNAT 3 indeed does encode a uniform distribution with, over the traces for 0, 1, 2, and 3. So now, what we would really like to claim is that UNAT n encodes the uniform distribution over 0, 1 to n in a very general way. So the good news is that we actually have something concrete now, and we can try to verify this out by hand using induction. The even better news is that we can automatically verify this using the press type checker itself, and this was very surprising to us when we first discovered this. So what we discovered is that refinements allow us to encode what we call a probing process to measure probabilistic properties. So here we have a UNAT PMF function. So the idea is that this function will take in a uniform natural number x, which ranges over 0 to n, and just an arbitrary natural number y, which is also selected through between 0 and n. So the important thing to note about this is that x is random, whereas y is arbitrary, but it's fixed. And all this UNAT PMF function is doing is it's doing an equality comparison of x and y. So it's going to return true if the number of successor messages it observes on x and y are the same, and it will emit false if it sees something different. So this is actually just doing what the probability mass function is doing in math. And we can see that through type checking, it actually verifies that our true message, which is the probability that our x and y are the same, is exactly the probability mass function that we would get in math. And this is another very surprising thing is that this entire UNAT PMF function is completely static. We don't need to run it at runtime, just by the fact that it type checks tells us that our UNAT encoding is indeed correct. And we can do this for even more complicated distributions. So one of the things that I tried doing was to do it for the maximum of 2 uniform distributions. I basically just had ChatGPT tell me the mathematical probability mass function. I copy and pasted it in, and I type checked. So now that we've seen how these distributions can be encoded, we can actually use these as building blocks for more interesting and more real-world facing protocols. So here we have a protocol for, or part of the protocol for a crowd forwarding protocol. So here we have a packet, which is essentially a type that's encoding a tuple using session types, and its layout is a message, a forwarding target as the second natural number, and then a final destination as the last natural number. And then for our R packet, it is a randomized packet, which is sending to a random forwarding target. So this it would be encoded as a UNAT. So the first thing that our node in the crowd is doing is that it is receiving a packet. And then depending on whether this packet is intended for our current node, it will either forward or accept in a provably sound way. So if it is intended for our current node, then we would accept and the protocol would end. Otherwise, if it's not provably the current node that's destined for this current node, we will repackage it as a random packet and then repeat the protocol. So now for our meta theory. So we prove that PREST possesses the following properties. It has type safety, that evaluation of PREST programs preserves types. We have global progress, where everything is guaranteed to be deadlock-free. We have probability consistency, that the distribution of communicated messages at runtime match the specification of probabilistic types. And we have an expected cost bounds theorem, which I didn't show today, that says the expected runtime cost of a program is upper bounded by its cost specification. So this is an extra annotation that we can add onto our types that tells us how many iterations that a function will run for. So for our implementation and evaluation, so the PREST type checker is implemented in OCaml following a bidirectional type checking strategy. So logical and probability constraints are generated during the type checking process, and they are exported to Z3. So the the constraints that we generate are using the nonlinear real arithmetic theory. So they are quite difficult to solve. So we evaluate PREST on a wide array of benchmarks. So we notice that despite the nonlinear real arithmetic constraints, Z3 performs very well, and all benchmarks are solved within 0.3 seconds. However, sort of the caveat to this is that this SMT solving is a bit brittle. Adjusting how these constraints are generated and encoded can sometimes blow up the solving time. We also notice that CVC5 is not as robust as Z3 for solving PREST, and that our constraint solving time does not necessarily scale linearly with our program size. For example, our Umax encoding solves very quickly, even though our Umax encoding takes a quite long time to solve when compared to our consensus coin protocol, which is much longer, but it takes less time. So for our future work and conclusion, so we want to apply this to reason about cryptographic protocols and differential privacy. We want to improve our constraint solving expressiveness and automatic solving with more relaxed notion of satisfiabilities. So such as we want to incorporate the D-real solver. This will make our probabilities a little bit less precise maybe, but we might be able to bound the sort of the loss of precision there. And also we would want to integrate ideas from probabilistic program logics. So with sort of the recent momentum on this front, where a lot of work is done in probabilistic iris, I think it might be also interesting if we can integrate ideas from these probabilistic session types into these probabilistic program logics. So in conclusion, we developed PREST for specifying and constructing randomized distributed systems. The integration of probabilistic and refinement types allows for a rich specification language and symbolic reasoning about protocols. PREST programs are formally guaranteed to behave according to their protocols, and a type checker for PREST is developed and evaluated on a variety of benchmarks. So the PREST type checker performs very well on many of these randomized protocols. So thank you.
Okay, thank you so much. We have time for one question while the next author goes to get his microphone. Yes.
Hi, really cool results. Do you know if PREST can be used to define sound generators for arbitrary inductive and co-inductive types? Because you showed the example for UNAT.
Yeah.
Do you think PREST can be used to do it for any inductive type?
I think so.
Like the user would just have to define
a
sound generator and it should work.
Yes, I think so, yeah. Because for PREST, we actually have full general recursion, so I think everything should work.
Cool.
But it might not be sound as a logic anymore.
Sure. Okay.
Yeah.
Thank you.
Okay, let's thank the speaker again. And now we have Haoshan Great. Now we have Shimcha, who's going to tell us about the backwards compatible row-based exceptions in ML.
All right, thank you. So I want to start with looking at type safety in the presence of exceptions. So normally type safety says that type programs cannot go wrong. But in the case of exceptions, it's a little bit more subtle. For example, we have the following program, which maps over a list of integers and always raises an exception. And then its type says that it is a list of integers, but there's no information in this type displaying the fact that this program raises an exception. So instead, in the presence of exceptions, what we're interested in is exception safety, which says that type programs cannot go wrong and also do not raise exceptions. Well, this is a property that you want for your whole program, but you definitely don't want it for individual components of your program, because, for example, the program here should definitely be type checkable as long as at some point the programmer handles the exception, and then in the end we know that the complete program does not raise any exceptions. So what people do to accommodate that is they make use of these rows to track exceptions. So we say that not only the program above has type list of integers, but it also has a row containing the singleton label error, indicating that the exceptions with the label error may be thrown. And then we say that a type program at an empty row cannot go wrong and also does not raise exceptions. So this has been done before. What we are interested in is designing a type system with this exception tracking, which is also backwards compatible. And with backwards compatible, we mean the following two things. First, we want programmers to be able to opt out from this exception tracking, and function signatures should be able to migrate it to this exception tracking one at a time. So the first point means that if a programmer has written an ML program and they now decide to switch to our type system with the exception tracking, then their program should remain to type check without any additional work for them. Second, let's say if a programmer has the following two programs where the first program is used in the definition of the second program. Now, what the programmer can do is generalize the type of the first program by adding exception tracking information. For example, saying that it raises exceptions in row. Then the second program should still remain to type check without the programmer having to do any additional work. So to come to our contributions, we have an ML-style type system with support for a bunch of regular ML features such as higher order references, polymorphism, concurrency. We also support local exceptions, which means that in ML, exceptions can be declared locally, for example, in the function scope, instead of what you have in other languages like Java, where you statically declare the exceptions which can occur in your programs. And of course, we have exception tracking. And we do this in a backwards compatible way, as we said before. And then we have safety and abstraction guarantees. So we have the exception safety statement from the first slide. And we formalize this all using binary logical relations via a relational separation logic, which has support for these local exceptions. And we mechanize this all in ROC using Iris. So in this talk, I'll mainly be focusing on the parts highlighted here in orange. So first, let's take a look at these row-based exceptions. So as said, we track these exception names via rows. So we either can have the singleton row, we have row variables which we use for row polymorphism. We have the first one is of course the empty row. The third one is the singleton row, which says that an exception with label E can be thrown, and then we can concatenate these rows. And then we annotate the typing judgment with these rows to indicate that the program E does not only indicate that it has type tau, but it also may raise any exceptions in row. And similarly, we annotate the function type to indicate that the function can throw any exceptions in row. And we also annotate the accent type, which is used to make exceptions, first-class data in ML. And then row polymorphism gives us stronger types to track these exceptions. So for example, we can have the following type for map, which says that if we have a function which may throw any exceptions in tau, then if we map this function over a list of alpha, then the output may also throw any exceptions in tau. Now this has been done before. What we have done is make this backwards compatible by adding a top row, which indicates that any exception in scope may be raised by the program. And this you can see as basically the default behavior you've got in ML. There you don't know anything about the exceptions that may be thrown. So we added this to the syntax of the rows. And then we get our backwards compatibility. So recall we wanted to programmers to be able to opt out from this exception tracking, and they should be able to migrate their function signatures one at a time. So the first theorem that we've proven is that our type system is an extension of a regular ML-style type system which does not have this exception tracking. So if you have a typing judgment without any exception tracking, then we can prove that we also can type check this program in our type system at the top row to indicate that we don't know anything about the exceptions that may be raised. And note that we have to translate these types here from the types that we use in the non-exception tracking setting to our exception tracking setting, which we do by annotating both the function types and the accent types with the top row to indicate the default behavior that you've got in ML. And second of all, our type system is designed such that we have the following property, which we call graceful generalization, which says that we can subtype interesting examples one at a time. So we start with a type which does not have any exception tracking, and then we show that via subtyping we can derive a type which does have exception tracking. So this makes the point clear which we had earlier, where we had two programs where the second program used the first program. If we now generalize the type of the first program to have the exception tracking, then we can show that it's a subtype of its original type, then we can still use program 1 in the context of program 2. Well, this is not a formal property, but we show for various interesting examples that we can give such a stronger type and its subtype derivation. And moreover, we can do precise exception tracking via rank and row polymorphism, as we'll see in the following example. So this example is one which we adopted from the Jane Street OCaml library. And it basically allows the programmer to program with a return statement just like you would have in an imperative language. So if we just take a look at the type of this method, we can see that if we want to construct some element of type alpha, then it suffices to only construct a closure which makes this alpha. But while we construct this alpha, we get access to a return function of type alpha to bottom, where this bottom indicates this return function never returns. And it's implemented using these local exceptions. So we start by locally declaring a return exception in the scope of this function. Next, we use this locally declared exception to create the return function. So every time this return function is called, it raises the return exception. We pass this return function to the closure that is given by the user. And then finally, we wrap this in a try-with block, which catches any return exception raised by the user. So anytime the user called the return function, the return exception is thrown, it's captured here, and then we can pass on the payload of the return statement. Well, if we want to have more precise exception tracking for this function signature, first what we should do is apply our extension theorem by annotating all our function types with this top row. And next, we want to be more general in the types of exceptions that may be thrown while using this function. So we allow the user to choose a row theta user, which they may want to throw while constructing such an alpha. And we annotate the function types with this to indicate that they are allowed to throw these exceptions. But now this is a problem because in the closure, you can see that the user is only allowed to throw exceptions in theta user, while internally the return function that they have been given makes use of an exception. And the bigger problem here is that the user does not even know which is the label of this exception, because it's only declared in the scope of this with return function. So we circumvent this by providing this exception to the user as a rank 2 quantifier. So the user gets given a row theta local, which is can be seen as the permission to use this return function. And it's given to the user since it's now a rank 2 quantifier. Then the user can now not only throw their user-chosen exceptions in theta user, but they are also allowed to raise any exceptions in theta local. So that basically means that they are allowed to use this return statement. If we then want to type check this function now with this more generalized function signature, we can see that we can now, after allocating this local exception, we can instantiate theta local with the singleton row. And then after the try with block, we can see that only the exceptions from theta local are handled. So we know that f return may throw either exceptions in theta user or in theta local. All those in theta local are now handled, and those in theta user are bubbled up as indicated by the output of this function. And more importantly, what we can do is we can recover its original type, which did not have the precise exception tracking, as a supertype of this more generalized type. By every time we see a quantifier on the right, we introduce it and then later subtype it to the top type. And every time we see a quantifier on the left, we eliminate it by instantiating it with the top row. Finally, we also have representation independence results. So just like local references, we want these local exceptions really to behave locally. So if we locally declare an exception E, and then we execute F, wrap it in a try with block where we catch all those exceptions in E, this should be contextually equivalent to just executing F, because E should not be in scope of F. Note that this is pretty similar to how local references are should be local. If we compare it to this more well-known contextual equivalence, which says that if we create a local reference and then execute F and then load R afterwards, then this should be contextually equivalent to just executing F and then returning 10 at the end. In the paper, we present a methodology to prove these contextual equivalences, which we do by providing which is based on a binary logical relations model. And the novelty here is how to semantically interpret these rows, where we have to make sure that the top row is not any exception which may be thrown, but precisely those exceptions which are in scope. And using this methodology, we can prove a bunch of examples. For example, we can show that implementations of a monadic map function, which uses a return, the with return example from previous slide, or the option monad, that these are contextually equivalent. And in the paper, we have also many more examples involving other ML features, such as concurrency, storing exceptions, and a bunch of other. And then again, this backwards compatibility gives us strong results. So if we can prove a contextual equivalence at some strong exception tracking type, then by subtyping we get also that this contextual equivalence holds at the weaker non-exception tracking type. So to conclude, we have a type system for exception tracking in ML-style languages, and we use row polymorphism, this top row, and subtyping to ensure backwards compatibility. We have safety and abstraction guarantees, and we have all proven this correct in ROC using Iris. So that was all I had to say for now. Thank you.
Thank you very much. We will now take questions for the speaker. Yes.
Do you have any plans to extend it to beyond exceptions to just to like arbitrary effect handlers?
Ooh, we did think about it. We did think about it. I think it seems like it's mostly or that you have to combine a lot of interesting features, which makes it hard. Another problem which we thought about was that currently how we prove this all correct is using this binary logical relation model, and in this setting with exceptions this is relatively easy, but once you go to effect handlers things become way more complicated. So we're unsure how scalable this is.
Thank you.
Yes.
Hi there, I'm Dan. Thank you for the nice talk. I was a little, maybe you can say something about type inference, because I was a little surprised you had the catenation on rows.
Mm-hmm.
And usually people use only like tail polymorphic rows,
Mm-hmm.
because that's easier for type inference. I don't know if you've thought about this or?
Yeah, so the type system is purely deductive. So we don't have any inference yet. We already thought about. We already encountered other issues, I guess, with type inference because our type system relies on this subtyping, and this already becomes a problem as well. But we haven't really thought that much about the syntax of our rows also because of
thanks.
that.
All right, let's thank the speaker again.
Okay, see what I've got. Okay, cool.
Okay. Okay, great. Next we have Songling Jia. He's going to tell us about type state via revocable capabilities.
Thank you. Hi, everyone. Thanks for coming. I'm Songling from Purdue University, and this is type state via revocable capabilities, joint work with my great collaborators. So first, what is type state? In simple words, type state means tracking the state changes of objects the same way we track types, statically at compile time. The classic example is locking. Languages like Java offer implicit lock management tied to lexical scopes. That's simple to use, but lock lifetimes are then forced to nest, so you cannot release a table while still working on a row. In contrast, by using lock and unlock methods directly, imperative code allows us to unlock the table as soon as we lock the row. So that's hand-over-hand locking, which offers better parallelism. By type state tracking on locks, we can further statically ensure that we never use resources without locking them. The next example is about building DOM trees. A tree is well-formed only when all tags are properly nested. The state we track is no longer a simple flag, but the entire stack of currently open tags. Here, we demonstrate the chatter catching two possible errors: closing a tab that doesn't match and closing when no tab is open at all. The tidbit here is that type state is not limited to a finite set of named states. It can track structured states like the stack and use it to enforce grammar-shaped invariants entirely at compile time. Our last example is about communication protocols or session types. The two ends of a channel must follow a protocol, a predefined sequence of sends and receives, and crucially, that protocol keeps evolving as the program progresses. In our example, the server keeps receiving strings until the client decides to quit, and only then closes the channel. Don't worry about the exact state transitions here, but the point is that we must track the channel state statically, even through recursion and branching. So we've just seen three quite different examples: logs, documents, protocols. In this work, we try to provide a single mechanism that covers all of them, revocable capabilities. Let me walk you through how it works. As a running example, you may only read or write a file when it's open. There are really two ways to write such code. First, in the direct style, you just call open, write, and close as you go. To make that safe, you need full type state, and people have already explored this for a very long time, from early whole program analysis to type state-oriented languages like Plate and session types. But the existing solutions tend to come at a price. They are tied to specialized languages or specialized domains, or they impose restrictions on aliasing using mechanisms like linear types and fractional permissions. Alternatively, in the scoped style, you wrap the file in a with file block, and now the only thing you need for safety is to ensure that the capability F doesn't escape the scope. That's a much lighter requirement, and several proposals have been made recently: second class values, reachability types, and Scala's capturing checking, the last of which is already running inside a mainstream language. So the natural question is, can this lightweight capability-based path be generalized to express full type state? Our answer is yes. Without inventing a whole new type system for Scala, we can describe stateful methods like open using a single signature, where that funny arrow in the middle explains the process. Reading it left to right, it does three things. It receives the closed state capability, revokes it to stop further use, and returns a new open state capability. Our receiving mechanism simply reuses Scala's implicits. Revoking requires an effect system that builds on reachability types and capturing checking. Returning a capability is our new extension and is implemented via a simple transformation. To see why this setup is necessary, let's build it up naively first. The simplest encoding is just to use different types for different states, an open file and a closed file as distinct classes. A new file is always closed. Open converts that file to an open file, and close goes the other way. Crucially, read and write require an open file. So already, the type checker guarantees that you can only write to an open file. The naive version already gets us a lot, but it has three serious problems. First, after close gives you a fresh closed file, the old fopen handle is stale, but nothing stops you from writing to it. Second, if you open file A, the resulting open file doesn't actually remember it's A, so you might accidentally write content meant for B into A. Third, because every operation returns a new handle, you are forced to thread a chain of freshly named variables through your whole program. These three pain points motivate our three pillars. Flow-sensitive revocation kills the stale handles. Path-dependent capabilities tie a capability to its object. And flow-sensitive implicits remove the naming burden. We detail these pillars in the next couple of slides. Pillar 1, flow-sensitive revocation. We annotate close with a kill effect on F, meaning that argument F is consumed. After calling close fopen, any later use of fopen is flagged as using a killed capability. That fixes the stale handle problem. The interesting part is doing this under aliasing. We use what we call descriptive alias tracking. We track sharing by names, so we impose only the minimum restriction. Such mechanisms include reachability types and capturing types. where destructive effects have been proven sound in the context of reachability types, and we build our revocation mechanism based on the experimental capturing type checker in Stella. The example below demonstrates such tracking. FC may alias with either FA or FB. When we close FA, the checker knows FC could reach the killed FA, so writing through FC is correctly rejected. Pillar 2, path-dependent capabilities. Instead of using different types for different states, we made capabilities abstract type members of file objects. So every file has its own isClosed and isOpen types. Then, using path-dependent types from dot, the calculus underlying Scala, a capability of type f.isClosed is provably about the file f and no other. So open takes the object f, and separately the isClosed capability C specific to f, and then kills only the capability, not the object. This path dependency is immune to kill effects from pillar 1, and it gives us a guaranteed link between the capability and the object it governs. So a write does not silently go to the wrong file. Pillar 3, flow-sensitive implicits. This improves ergonomics. Half of it is already in Scala. Instead of passing the capability by hand, we mark it with using, so the compiler finds the nearest implicit candidate, and you just write openf. The new half that makes implicit really flow-sensitive is their returning. The treat here is that when a function returns both the data and the capability as a dependent pair, or we call it sigma, our inf transformation kicks in and extracts the second component as an implicit candidate for the rest of the block. So after assigning the result of new file to f, the isClosed capability is silently available, and the next open just picks it up. No more threading chains of renamed variables. The program reads like ordinary imperative code. Putting these 3 pillars together, here's the payoff. We support all our motivating examples with the same mechanism implemented in Scala. The file operations now read top to bottom on a single variable f. The same mechanism handles hand-over-hand logs, building well-formed DOM trees and binary session types where recursion and branching exist. Now, what this buys us in real control flow and what it costs. First, the easy case is when control flow doesn't fork the ending state. Using a capability repeatedly needs no special treatment at all. Here we write to f inside an ordinary for loop, where each iteration leaves the state unchanged. Likewise, a plain if then else is fine as long as both branches land in the same state. In this session types snippet, both the then branch and the else branch fully execute the protocol and closes the channel. So we just use a normal if. So the takeaway is a lot of real code needs 0 extra work. The harder case is when branches end in different states. We handle this by reifying the choice as either capabilities, and we offer combinators to work with them. Our if combinator runs one branch, for example here, leaves the file open, and another branch that leaves it closed, and its result is either of is open and is closed. The state becomes data. Joining is a duality. A matched combinator inspects that either implicitly, and in each case, the capability is recovered with the right state. So both cases can now converge here back to being closed. Combining fork and join gives us state-dependent loops. The while combinator here, for example, keeps iterating until the ending state is reached. The iterator is exhausted. So even non-trivial control flow stays expressible and checked in our framework. What does it cost? We measure the DOM tree examples, and the key message is the overhead of capturing, checking, and our effects is comparable to the compiler's other phases. It's not a blow-up. On the left, the ablation at fit steps of 17 shows that capture, checking, and effects contributing a reasonable slice over the baseline. On the right, stating the depths from 17 to 33, the effect phase grows, but stays in the same ballpark as typing and the rest. So the approach is not only clean, but also practical. To wrap up, we bring type state to Scala and to general settings, by treating stateful programming as receiving, revoking, and returning capabilities. We get autonomic control flow and impose only minimal aliasing restrictions. Our 3 pillars include destructive effects for revocation, path-dependent capabilities for tying state to object, and the new ingredient is that implicit return values via NF transformations. We validated our framework on files, logs, DOM trees, session types, and control flow combinators, and our artifact is available online. Thank you very much. I'm happy to take any questions.
Okay, thank you very much.
Hi, thanks for the talk. Big fan of capabilities. I wonder if you can speak about the revocation aspect and what that's doing for you here, and whether this is a mechanism for something like consuming a linear resource, and how you are you thinking, or like how are you doing session types within this context of Scala, and are you thinking of doing linear typing with this, and are you able to recover this from these mechanisms? Thank you.
Yeah, great question. So of course, revocation would naturally make people think about linear types, and naturally you can do some type-state programming in linear types. But the point of what we are doing here is that, so revocation or moving resources or moving capabilities or consuming them should be optional. So later in this talk, I showed an example like you can summon or using capabilities in a loop. So that does not constitute any of the usages or consuming at all. So that's simple using. Whereas only for such, when we are really invoking a state transition, we must want to consume that capability for someness. So our revocation here, you can think of understand it in the way similar to linear types, but consuming is only optional in our setting. That's for the first question. For the second question about session types, let me see if I can get to the example. Yeah, so here, so basically we have to annotate, we have to track the protocols, session type protocols basically, as a type abstract type member, like I said, in some field of the channel protocol. So basically, you can think of this as a real type signature for this. For example, the first red push is like, it is transitioning the channel.ptab. So ptab is a capability type, and ptab is parameterized over this red receive you are really seeing. So that's the session type. Yeah, hope this makes sense to you. Any other questions?
Okay, let's thank the speaker again.
Thank you.
Next, we have Tim Whiting speaking about syntactic implicit parameters with static overloading.
Hello, everyone. My name is Tim Whiting. I recently graduated from Brigham Young University with my PhD, and this is joint work that I did with Don Lyon from Microsoft Research, and we'll get right into it. So the motivation behind this talk is implicit term inference. And really, we care about this in order to reduce the noise of our programs. For example, if we want to convert a list to a string, we're going to need a function to show the list, as well as a function to show each of the elements of the list. And obviously, this can get quite elaborate very quickly with needing to show tuples that have multiple type parameters. With Haskell-style type classes, we can simply write show and then the list, and the compiler automatically adds those dictionary arguments for us based on the types. We were interested in whether we could simplify. Obviously, type classes are very elaborate, and very nice, but there's a lot of machinery that goes along with that. So our work combines three orthogonal ideas. The first is that every definition can have a locally qualified name so that we can refer to each definition unambiguously. The second is that static overloading is a strict elaboration from plain names to a qualified name, and that is based on the type context. And then the third ingredient here is syntactic implicit parameters, which are parameters whose unqualified name is inserted automatically at the call site and resolved in the local scope. So the first idea here is to use locally qualified names. Just like in most programming languages have module names that we can scope definitions in, we allow those qualifiers locally as well in each of the files, and they can actually have as many local qualifiers as you wish. All of those fully qualified names uniquely identify definitions. So in the example test explicit, we can refer to the character MyShow definition. Obviously, this is still very verbose, kind of antithetical to what we were hoping to achieve. But you'll see how this leads into our other ideas. The second idea is that static overloading is just an elaboration on names, just qualifying those names. And we do this based off the type context. So for this definition of MyShow, with passing in the integer 1, we're going to discover that based off of the local type context, we want the int MyShow definition. And we can do the same thing for character as well. So this is similar to C++ or Java style overloading, where we are determining which overloaded name should be referenced based off of the types and the arity of the function. And it's also similar to static multiple dispatch. The primary difference from type classes is there's no upfront class declaration with signatures of all the functions involved in the overloading. Unfortunately, we run into the problem of abstraction. So if we want to show a maybe type, then we're going to get stuck here in the MyShow definition in the body. And this is because the type variable A is still abstract at this point, and we do not have a corresponding overloaded definition for an abstract for all type. And Coca will give us this error that the identifier MyShow cannot be resolved, and give us some candidates and suggest qualifying the name. But how are we going to solve this problem of abstraction? The first thing that we're going to do is we're going to reach into our functional language toolkit and pull out the regular higher order function abstractions. And here we add this MyShow parameter from type A to string. And then now MyShow is fully understood in this local context to refer to this MyShow parameter. Now at the call site, we need to provide that MyShow function, and notice that there are no qualifiers needed. So this will automatically elaborate to maybe MyShow and int MyShow based off of the type context, the local type context for just 42, which instantiates the type variable A. The third idea is that implicit parameters can be resolved completely at the call site purely by the name of the function and the local type context. So in order to do this, we're just going to add this question mark syntax to the MyShow parameter, and then we'll let static overloading add the qualifier for the maybe MyShow method, and it will see that we need to add the implicit parameter MyShow. So this will be automatically elaborated to this, and then finally the static overload for int will be added. So this seems very simple. All of these mechanisms are very simple, and they're very orthogonal. But together, they give us powerful recursive interactions. So if we want to show a list of integer lists, we're going to qualify. We're going to add the implicit parameter. We're going to qualify again. And this next step is a little tricky because we're going to eta expand the function in order to provide the next implicit. In the actual paper, we formalize this a little differently by adding implicits at the beginning of functions and allowing for currying, so we don't have to do this eta expansion. Then step 5, we're going to qualify the inner int myshow. So if you try and port your standard library using this, you're going to run into an issue once you have multiple type variables. So in this tuple myshow function, we have alpha and or a and b, and in order to properly distinguish between these two myshow functions, we're going to reuse our trick from before. We're going to use local qualifiers first and second. And so with that, the compiler and the type system has enough information to properly distinguish between which myshow should be referenced for x and which one for y. Now we can write at the call site just a regular myshow or tuple myshow, and the compiler will add in both of the myshow arguments, and then those will be determined based off the local type context to int myshow and character myshow. Note that we define those implicit parameters with additional qualifiers on the name, first and second, but we always resolve the unqualified names at the call site. So we're going to unqualify it before we add the qualifiers and elaborate out here. And that's important because in here, in the local context, those are needed to distinguish, but the name itself is important and not the qualifiers in the outer context. Some advantages of our system is that it's a purely convenient syntactic elaboration. There's no additional semantics to the language. This is also could be seen as a disadvantage compared to type classes, since type classes guarantee uniqueness. The programmer also can always explicitly qualify a name or provide an implicit parameter. There's no hidden mechanisms that can't be worked around. And this is interesting because in Haskell, you need both a sort and a sort by function. The sort takes the default comparator, and the sort by takes another comparator. But in Coca, we can just add, give the implicit parameter explicitly at the call site to use a custom comparator. Additionally, there are no new semantic concepts like type class or instance, or special scopes like implicit scopes. It's all just names and functions as usual. And that also admits a very straightforward implementation. We don't have constraint solving and all of that extra machinery. We just need to augment the name resolution and application rules. And this is nice for an ID as well, since we don't have any hidden dictionary elaboration, and we can just show the regular elaboration in line. And we're going to go to a quick mini demo to show this. So if you open VS Code, you can install the Coca programming language extension. It will automatically prompt to install the compiler, and you can test this out for yourself. Here's that show function with a list of lists. And as we can see, if I hover over it, it will tell me that it has resolved to the list show function, which has an implicit parameter show, and it will show me the chain of implicits that was required to resolve this function. Additionally, with inlay hints, we can also show that elaboration in line, and if you want to be explicit about it, you can double click that, add it in. Is it showing right? Okay. The next thing is that you might be wondering, what's the difference then between syntactic implicits and type classes? What additional power might we get, or what additional constraints might we have? So one big difference is the need for upfront declaration. We do not need to declare the signatures upfront, which allows us to overload any random field, like first for tuples. We don't have to have the same signature, and this is system O style overloading. But unfortunately, we also need to be very explicit about implicits. So this function right here with the show and the will complain at us because it won't know which show function we mean. Of course, we can provide that explicitly. If we have a particular definition of show in mind, Haskell will automatically infer the show constraint for us. But in Coca, we have to add that implicit parameter explicitly. And this is kind of a difference between focusing on the term inference and rather than the type inference. We care about inferring those terms more than the types. Our implementation also allows for special names that are manufactured by the compiler, such as kkfile, which elaborates to the current file. And we can abstract over this mechanism using kkfile. We have formalized this and have principal type derivations, soundness of elaboration, as well as stability. And we formalize this building on previous work, type inference under prefix. And this is really important because we need to precisely define what the type contexts and the environments that should be in scope and are used for resolving implicits. And just quickly on the soundness of elaboration, this definition right here is to translate types to implicit parameters, from implicit parameters to regular Hindley-Milner types. Our types with implicit parameters include names. And so really all that is removing those names from those types. And it elaborates to just a regular lambda calculus, which Coca uses. And stability is an interesting property as well, because when we inline, the type context changes, and we need to know that the elaboration should be the same. The final formalism aspect of the formalism that we're going to mention is termination. The really interesting thing about this recursive interaction between these very simple mechanisms is that they can encode a Turing machine. We present a novel and predictable cutoff, and it's basically that we recognize that the same definition, we have a finite number of definitions, and the same definition would have to be gone through multiple times in order for us to not terminate. And so as long as the instantiated type that is required decreases in a bounded manner, then we can ensure that the type system will eventually terminate. And the interesting thing about this particular cutoff strategy that we chose is that we can still encode a three-state busy beaver in the type system by encoding Turing machine transitions in the type system. And this is the actual implicit elaboration or implicit chain, showing that trace of execution. So here we have the transition from state A to state B, then B to A, then A to C, and so on all the way to the halt transition. We also show that the finite rules are sound with respect to the infinite ones. And this is really subtle because if you just do a cutoff naively, you might just assume that the unique definition that you found should be the implicit. But if you cut off early, and there could have been other, if it could have been ambiguous if you considered at all depths, then you would be unsound. And so you actually have to take into account the ambiguity there. Of course, in practice, we also want helpful features like grouping together signatures. And we can do that as well, just using regular structs. And we add this additional syntax with the dot right here, which we call the implicit unpacking operator. And all that does is insert a match at the beginning of the function, which unpacks those fields and calls those fields by their exact name. And so this is just another syntactic trick and a using basic syntactic scopes. And that's all I have. Any questions?
Thank you very much, Tim.
Yeah, so you said that like the resolution of implicits is, I think you used the word stable over inlining when you gain additional type information.
Yes, so the stability property, maybe I stated it poorly. Maybe Don can help me with this. This is that if we instantiate the environment, or if we apply substitutions to the environment, then we will elaborate to the same expression.
How does that work when, I mean, presumably the static overloading for a function like first, you'd probably only have one first that's generic over pairs, say, but you could, is there anything stopping you from having an overload that involves like a pair of int and float that's sitting there competitive with the non-generic, with the generic overload? So
part of the idea of the static overloading is that that the resolved definition must be unique. So there only can be one definition. So it comes out, the stability really comes by default from that aspect of we're considering the lexical
so the
scope.
Overloads always have to disagree in the heads of the types involved or something like that?
They always have to be unique. We don't just consider heads, we actually search the whole depth.
Okay, so
criteria.
they just can't overlap and then...
Can't overlap.
Okay,
yeah.
Thank you.
Any more questions? Okay, let's thank the speaker again. And this concludes our session. Thank you very much.